There we go. Freeform steel and glass facade construction is a typology that's been just increasing in popularity over the past 20, 30 years. Freeform facades as a kind of design tool for architects can be applied for a number of reasons. At one end of the spectrum, we have the kind of more sculptural or poetic endeavors. And at the other end of the spectrum, there's a number of really practical reasons why these types of systems might be applied. One of them being that a lot of kind of structurally efficient geometries are inherently freeform. The use of glass as a material obviously allows us to bring a lot of light into the space. The use of steel as a substructure material, because of its high strength and its high stiffness, basically allows us to have maximum transparency, long spans, elegant profiles, and just overall highly transparent and very elegant enclosures. And when we're talking about steel glass facade systems, we're generally talking about layered assemblies. So you'll have your layer of steel, your interior drainage, your glass, etc. And each layer within this assembly has its own kind of performance, and the performance of the overall envelope really relies on the integrity between these different layers, and also the integrity of the connections within the elements in each one of the layers. And in standard applications, this is really easy to accomplish, right? We have these mass-produced components. We use standard tools to have standard connections, and everything comes together really nicely, really smoothly, really easily. But this gets complicated when we start talking about freeform applications. All of a sudden, the geometry at these intersections is significantly more complex. And somehow, we still have to treat these intersections in such a way that none of the performance is jeopardized. And this challenge is made even kind of, or is compounded by the fact that in a given project, you might have hundreds, thousands, tens of thousands of entirely individual, unique conditions. And this requires, especially when it comes to, for example, the interior drainage layer, this might require a lot of kind of careful cutting, gluing, manual high precision labor on site in order to avoid having leakage and other performance issues. When it comes to the structural nodes, as an industry, we've come to rely on a lot of computer-aided manufacturing for mass customized solutions. But the computer-aided manufacturing methods that we have available basically have not allowed us to reach design efficiency and material efficiency and fabrication efficiency. So there's always kind of a little bit of give in one of these areas. And so what we strove to do was to overcome this by developing what we now call the VIS cube system. So where the VIS system is the standard Janssen commercially available facade system, the VIS cube for us refers to an additively manufactured intervention only at the nodes, only at the intersections where that geometry is particularly complex. And that consists of a structural node and also, as Nadja mentioned, the gaskets. But today we'll be focusing more on the kind of the structural node and the development and the journey that we've been on for that. And what this strategy allows us to do is to take advantage of all of the efficiencies of commercial facade systems. And yeah, like I mentioned, concentrate the use of additive manufacturing really at those intersections where we need to leverage or we need complex parts. And so what we strove to do was to come up with a system that is fully standardized. Standard interfaces, standard connections, and also standard geometrical approaches to all of our components. We also wanted something that's entirely parametric, so all of the components are parametrically driven, and that the parameters that we allow ourselves to kind of manipulate and integrate into our designs allow us to reach that level of fabrication efficiency and design efficiency and material efficiency that we're looking for. And we look to additive manufacturing for its strengths. Obviously, the geometrical freedom that we get for additive manufacturing is something that designers can leverage to be a little bit more ambitious in terms of the design of their nodes. It also can help us get more material efficiency. We look to additive manufacturing because the material properties can be excellent, and because it's another method of computer-aided manufacturing. So we can go very smoothly from our parametric, mass-customized digital design processes into mass-customized digital manufacturing. But yeah, the realities of working with additive manufacturing are such that depending on the technology that you work with, there are different strengths, different limitations, and just different realities depending on the method that you're printing with. And so the first step in this kind of exploration, and this is really what it was an exploration, was testing out what it actually means to work with these different metal printing methods. So what you see here is the first prototype that we built, where we have 3 different nodes, each printed with different additive manufacturing methods, and also each designed specifically for that additive manufacturing method. So we worked with powder bed fusion, laser-based powder bed fusion, laser-based directed energy deposition, and also gas metal arc directed energy deposition, which a lot of you might recognize as WAM. So the first node that we designed was for powder bed fusion. Because it's kind of a very slow, intense printing process, our intentions were clear. We want to minimize the amount of material that we're printing, and we want to concentrate that material in the actual structural component rather than having a lot of that printing time going to printing to supports. So what we came up with was a design where we have basically 2 sets of interior walls. One that's following the kind of main directions of all the members that are connecting to the node, and another set of concentric cones in the middle that essentially just distribute the forces via membrane action in the middle of the node. And the wall thicknesses of these nodes are adjustable based on the specific structural requirements of that particular node. And all of this wall structure is roughly aligned to the building orientation of the print. So there's actually very, very little support structure needed in this design. The next technology that we worked with was WAM. And for this, we developed a node that has a kind of hierarchy of arms. So primary arms, secondary arms, and tertiary arms. And that hierarchy refers to the kind of hierarchy of loads within the node, but then also corresponds to the printing process. So you can see kind of the order that things were printed in embedded in the texture of the node. Each of these arms has 4 plates, 2 outer plates, 2 inner plates, and then the inner plates meet in the middle. And with all of these plates, we're able to address all of the loads, so the shear loads, moment loads, normal forces that we need within these structural parts. And then on the outside, because we wanted these kind of flat faces where we could have our standard connections, we gradually increased the thickness of the arms such that we could have that flat end face. And then after it was printed, we took it down, we milled the ends, we milled the kind of connection features that we needed to add it to the mock-up. And yeah. And then the next technology that we worked with was the laser-directed energy deposition. And because, like I said, it was an exploration. And we decided to take a completely different approach, even though we could have kind of went with a similar design to get a apples-to-apples comparison of the 2 technologies. We decided to try something kind of entirely different. So for this design, instead of starting with a substrate and then building up from it, we decided to integrate the substrate directly into the print. So in this case, we've got a cylindrical substrate, and we're essentially just printing radially around that substrate. And one of the kind of main advantages of this particular design is that the technology that we worked with, or rather the specific machine that we worked with, was an additive subtractive machine. So that allowed us to very efficiently build up the part and machine it in the same machine setup, in the same cam setup, and that ended up being a kind of, important feature for this particular design. So now I will pass the podium to Matthias, who's going to talk about the next step in the project.
Thanks, Leah. Yeah, what we see here is how the mock-up was installed. I will explain some things regarding the workflow when we design freeform facades from the perspective of structural engineering. So that is pictures from, I think, 2006, Westfield in London. The nodes are consisting of single plates and pieces that are welded together. And the geometry of this whole freeform structure is generated by the geometry of the node. So the beams are pretty simple. They just have straight edges, but the complex thing is the node, and therefore it makes a lot of sense to concentrate on the node and on the geometry and how to fabricate it, because that's the important thing. And on site, that's what the companies are doing. So members and nodes, and in this case it is just bolted, and Thorsten Helbig's explaining on site it's just a monkey job to bring these pieces together. So that is not rocket science. Rocket science is in the node, and there is, if you look in the past how the nodes could look like, there's a lot of different examples depending on the geometry and depending on the profile dimensions, open or the famous mirror one. What metal contractors do in these days is more or less this. So the node is milled out of a solid piece. So that means we have a lot of material which we don't need. And now it's coming to additive manufacturing, and this gives us new opportunities in respect to how the node could look like. And in our example here, in the collaboration with Janssen, we were at the point, okay, what do we want to do for the first mock-up and the first thing? So, and we decided to have a node where the secret is invisible, so we are not showing how the things are connected, and we are not showing how the node looks from the inside. So that is the first approach, but that doesn't necessarily mean that for each project it needs to be like this. We could also in the past proceed, and it could be that at a certain point of time there is freeform structures looking like this. The workflow for our small facade is similar to what we do for huge facades, like the roof here for my side in Frankfurt. So it's coming from the surface that we received from the architect, in this case Fuchsas from Italy. Then we need a structural model. It comes to information for fabrication and then fabrication, and we have the product in the end. So as said, it's similar here. We have the design surface. We need to analyze the geometry. This is important because we have some restrictions in respect to the geometry. We cannot fabricate or get the facade watertight if the angles are too small or too big. So there is restrictions, and if we want to use quadratic or rectangular glass panels, there is further restrictions in respect to geometry and curvature that we need to consider. So that's what we did here, or actually Leah did that in the beginning. And then from the surface, we need to create a beam model. And in these days, Grasshopper is always involved in these tasks. And then the most important step in respect to structural analysis and how things are coming together is happening here, where we need to play things and information back and forth. So we will figure out what is required in respect to dimensions of the node and so on, and that will then influence some global parameters. Maybe we need to rethink things and change geometry of nodes, or maybe sometimes also of the surface. So that is going back and forth here. And then at structural engineering, so finite element models, one thing that is important for us, so we are using steel, but the steel that is used to print these nodes is different from typical steel. So we need to run tests in this case in order to figure out what is the isotropic or anisotropic material properties, and that was considered then in our structural calculation. And once calculations are done, we, or Leah in this case, again, did create tables with the parametric information that are used for fabrication then. And I pass over to Leah again.
So in the end, everything was fabricated from the outputted information from the definition. Everything came together really smoothly. No issues related to tolerance or anything like that. So it all came together very nicely. To conclude, this mock-up allowed us to do a number of things. First, it was for us a kind of validation that our geometrical approach worked, that our approach to using that additive manufacturing technology worked. And it kind of allowed us to showcase and test if all the geometrical conditions that we might face one day that we could take on with this system. So you've got anticlastic curvature, synclastic curvature, positive and negative. So all of these kind of tough geometries we built into this wall to test whether or not we could do them. And the other thing that it allows us to do is to start to develop a workflow for what it actually means as a team of building industry professionals to work with additive manufacturing. So there's a lot of different professions involved in this task. It's a very multidisciplinary effort. You've got the architect, the designers, the structural engineers, the system house, and then you also throw in the additive manufacturing experts on top of that to make sure that you're really leveraging each technology in the best way for your specific design, for your specific application. So that was a very kind of important step for us in working towards the use of additive manufacturing as a possible solution for freeform steel glass construction. So I thank you for your time and attention, and happy to hear your questions. And if anybody wants to see the mock-up, it is in Hall 11 at D68. D68 if you want to see the full construction. So thank you very much for your time.
Hi, great presentation, thank you. I already saw the mock-up, they look amazing. I have multiple questions about this. So my first question is, in the end, like you kind of changed with the laser welding, you kind of changed your approach. I was wondering if you could also imagine this for an SLM print and a WAM print to go in a direction where you don't fully make the knot, but kind of work on a piece itself. And then the most important question is, who actually printed these things? Is it all the same contractor, or did you print it, or there are not so many people on the market that can actually provide all of these three technologies?
Sure. So the WAM technology, to answer your first question, so the wire and arc additive manufacturing could have also been used for a similar design to the one that we used here. SLM to integrate the substrate is a lot harder. I actually don't think it's possible, but maybe don't quote me on that. And then, we worked with a number of different people to get these things printed. So the wire and arc one, we cooperated with MX3D, and they were the kind of first collaborative partner. And then for the SLM print and the DEDL print, we had a printing partner in Austria who, they were a small kind of metalwork shop, and they had the 3D printing technology, so they did both of those. And then we also printed one of the SLM prototypes at the TU Delft. Okay. So here and there and everywhere.
One more question. Did you get certification for this? Like, is it going to be a project, a certification, a unique case, or is it for now only research?
So, I mean, we got project-specific approval because we had this up at GlassTech, but in terms of kind of general approval, that's the next step. So the next step is going to be looking forward to how we can certify these different parts and products to actually get them in buildings. The first one is probably going to be a project-specific approval, and then but mid to long term, we're looking to get everything fully certified if we can.
Okay, let's talk later about this.
Hi, thank you. Great presentation, by the way. I have a more structural question. Did you consider, or how did you calculate the stiffness of the node? Like, is it a rigid node, a rigid connection, a pin connection, mixed?
It's a rigid connection. Yeah, and we don't think that's understandable. We don't want to show how the things are connected at this point of time. But it is a rigid connection.
Okay, thank you.
Well, if that's okay with everyone else, we're going to take a few minutes for everyone to get a coffee or something to drink. So as Philip pointed out, please keep it short so that we can listen to the next presenters in a few minutes. of Menskorte, Ingenieur und Architekten. So he knows both the design and the business side of additive manufacturing and construction. He's here to talk about digital fabrication in 3D concrete printing. And he's going to show us a little bit about the transfer of concrete printing to construction industry with the first 3D printed house in concrete in Germany, which is a joint realization from Menskorte and Peri 3D. Waldemar.
Thank you very much. Okay, first of all, that's the first presentation I'm going to have in English, so I'm quite nervous and a little bit excited too. So I have these slides here. I'm going to read some of the points, just not to, just to be able to have the presentation the way I want to. Okay, good morning, ladies and gentlemen. My name is Waldemar Korte from the engineering office Menskorte from Beckum. Our office designed, developed, and built the first printed residential building in Germany, together with the scaffolding and formwork company Peri and the materials supplier Heidelberg Materials. Today I would like to give you some insights into the first printed building in Germany, which is based in Beckum, and explain the planning process in 3D printing of buildings. Oh, okay. Well, let me shortly introduce myself. Before I started studying architecture in Münster, I became a bricklayer in order to gain practical experiences in the building sector. After my studies, I started working at Mensa Werner Bayer and became one of the owners in 2015. In connection with the realization of the first printed building in Germany in 2020, we decided to found Menskorte. So it's the same company, but another name. I divided my presentation in 3 points. The first one is the choice of a 3D printing process method we wanted to do, the BIM planning in 3D printing, and the last point is some impressions from the finished building in Beckum. First of all, I would like to speak about the printing process we chose for the project. The contour crafting procedure is well known among 3D printing professionals, as you all are, I suppose, because it represents the most promising type of printing large structures such as buildings. While I know most of you know more about contour crafting than I do, I want to give you a quick overview of how it works. So for most of you, it's nothing new, but it's just to complete the whole process. Okay. Contour crafting. When it comes to contour crafting, we put viscous building materials such as concrete, sand mixtures, and clay. They are built up over a scaffold by a mobile robot, layer by layer, based on a digital 3D model. So that's nothing new for you. The concrete mortar is extruded as fresh mortar through the nozzle via a screw conveyor, not in the pressure head, but in the print head. That's a mistake. And laid down as a layer of mortar with a pressure thickness and width. The route specified for the printer comes from the Planet 3D building model. So that what you see here is one of the first printing parts in the Beckum project. And you see the route for the printer, which comes from the 3D model we designed and developed in our office. Two main components are essential when we talk about 3D printing of buildings. The first is the printing material, and the second, the printer itself. Let us first take a look at the material. The printing mortar is not standard concrete because it must have several properties that normal concrete does not have. So if the material is hardening too slow, so that's the left picture you see, you get a good adhesion of the material itself, of the layers, but the mortar is sagging and you get non-uniform layers. So that's nothing we can build with in the construction sector. If the material is hardening too fast, you get uniform layers, that's great, but you get a bad adhesion, what leads to bad static properties of the whole construction. The optimal way is if you have uniform layers and a good adhesion between the layers. So that's the optimum. So you have to take care of the layer time you use for these constructions. We worked with the material of Heidelberg Materials, Heidelberg Cement, and the connected firm Italcementi from Italy brought the material to us. The material properties have to be, as you see it here, the material has to be pumpable, it has to be well extrudable, it has to be dimensionally stable at an early time, but it has to be long enough open to connect to the former layers. So that's what you saw the pictures on the left. The printing machine is no less important than the material itself. The Beckham project was printed with a Cobot printer. Cobot is a firm in Denmark with E, which developed the machine in 2018. Perry is a Cobot joint venture and offers the printers for rent and for sale in Germany and other countries around the world. The print head moves around the 3 axes in a permanently installed metal frame and can reach any point in the print room. So the building we have got has to be based in the printing room. So the printing room shows how big a building can be printed in one. The maximum span of this printer from Cobot is 50 meters wide, 70 meters long, and 9 to 10 meters high. So that's the maximum you can print at once. If you want to print bigger constructions, you may move the printer. That takes about 1 day to remove the printer and to install it and to begin the print on the next day. So 1 day is enough for that. And if you do not want to remove the printer, it's possible to make it a little bit bigger because this whole system is modular. It's modular in the height, it's modular in the length and in the width. The next point I would like to talk about is BIM planning and 3D printing. So that's our main topic for us as architects. I'm an engineer and an architect, but I'm not a scientist, so I'm just concentrating mainly on this topic, planning of 3D printed buildings. Here you can see the floor plan of the Beckham project. The beginning of the planning process is relatively similar to common projects we know. First, you develop the floor plan together with the client. The first ideas could be drawn by hand on a piece of paper, so it doesn't matter. In the next steps, you start designing the building in CAD software. The 3D model will be essential for further planning steps which follow in the process. In 3D printed buildings, we plan the wall structures of different multi-layer wall elements. So that's what you already see here in this drawing. For the Beckham project, we decided to combine mortar lines which were 6 centimeters wide and 2 centimeters high. The printed walls are able to carry vertical loads from the slabs and horizontal wind loads. In addition, we had to add in situ concrete without reinforcement and cavity walls to complement the engineering concept, just to consider the safety aspect of that building. Because this building we constructed in Beckham is completely permitted, so it's, there's already a person which lives in that building. That's not just a prototype. So it went into reality. It was, okay. So what are the next steps when it comes to planning of that building? The 3-dimensional architectural model is provided with a lot of information. The technical trades have to provide their input at a very early stage of designing. The 3D model should be filled with information on reinforcement, outlets, and routes for technical trades. So that's what you see on the next picture. Here you see all the reinforcement in the in situ concrete, for example, in the slabs or in the columns you see here. And you already see all the pipes for the ventilation we had in that building, which are also included in this BIM model we developed in the office. Technical features of the specific printing process must be taken into account, such as the freedom of movement of the printhead. So it depends on the printer you have, it depends on the printhead you have. A hindrance of the printhead by reinforcement is to be avoided, and special elements such as lintels, cantilevers have to be considered. So all the different construction elements, all the different details had to be developed by us, because there's no book where you can have a look how such a detail works. You have these books for masonry, you have these books for common concrete or normal concrete, but not for the 3D printing of buildings. So we had to invent to develop all these details. So the next step you see here is from our architectural 3D model. You have to convert that building into a centerline model, because the printer only understands, or the slicer software of the printer only understands the centerline model. So we have to transfer our model into a centerline model. In the centerline model, we check the files. If everything really matches well, we fix errors. If there are some in the file, we are fixing gaps in the model. And then when everything's done, we have to subdivide that model, that ground floor, in different printing sections. Because of the layer time of 15 minutes for the Heidelberg material, we are not able to print the whole ground floor in one step, because otherwise we would leave the layer time, and that's why we have to divide this building, the ground floor. You see different sections here in the different colors. We had a minimum 2 sections, but here we decided to have 3, because just to be on the safe side, so we have no problem of leaving the printing layer time. This picture shows an extract of the printing section, of the first printing section. So that's a picture of the slicer software from the machine supplier Cobot. In this software, you are able to generate the travel moves automatically, but you also can change them. You are able to optimize the travel moves. So sometimes it's necessary to optimize them, because the program is not that clever that everything is considered we want to have, or we need to be considered. You can define the layer thickness, you can define the print speed, the layer time can be defined. And at the end of the day, you generate a G-code and transfer this G-code to the printer, because the printer only understands a code of numbers and not this centerline model. And that's the time when it first comes to the printing process itself on the job site. During the printing, there are also some adjustments which can be made. So you are able to adjust the printing speed, you are able to adjust the extrusion factor just to react to the environmental conditions, for example. Sometimes that's necessary. You are able to adjust the thickness of the layer. And in case of malfunction of the machine, what can happen, what often happens, not often, but can happen, you are able to get back to the recovery point where you stopped the printing, where you stopped the printing. You can activate the recovery point and continue printing at the same point where it stopped. So you do not have any gaps in the print itself. Here you can see some examples of the advantages of 3D printing in that building in Beckum. So because we integrated all the different trades in a very early stage of planning of the building, we were able to consider all these wall openings for electrical trades or for plumbing, for example. We were able to install the electrical sockets during the printing process. They are installed manually, but the printer leaves these cutouts in the wall. So there is no material where it's not needed, so you can pull the sockets inside. Another advantage is that you are able to print fixed installations like a fireplace, for example. So we integrated a fireplace in that building, And everything which is fixed in a building can be printed, because you're not going to remove these parts in a few years, so you can print them from concrete. And another point is you are able to print lost formwork for the in-situ concrete, which we needed for the statics for that building. Here you can see a reinforced column. We also just wanted to try out if it's possible to integrate reinforcement in the 3D printing process. So it is possible, but you're not able to, the reinforcement mustn't stuck out, because the print head cannot move around the reinforcement. It's in the way of the printer head. So you have to work with a kind of reinforcement which can be screwed in. You know what I mean? Okay. And that's a possibility. So you're going to print 1 meter high, then you screw in the reinforcement, then you print the rest of the column, and then you insert the rest of the reinforcement from above into this column, and that's when the column is reinforced. You just put in situ concrete in it, and then it's ready. And it doesn't matter which geometry this column has got. Because of the 3D printing process, you are extremely free in designing such columns. On the picture on the left below, you see a pattern in a facade. So that's the next advantage we have. We are able to print in patterns into the facade without causing additional costs for the client. That's a big plus point for the 3D printing. And we just tried out everything in this Beckham project, what you can see here. And on the right side, you see a colleague who is inserting the insulation into the hollow walls we printed. And this insulation is made of perlite. Perlite. It's a volcanic material. It's a natural material which can be removed easily after the life cycle of the building. And last but not least, here's the nearly finished printed building in Beckham. As you can see, we printed nearly everything what's printable. We printed the not load-bearing walls and the load-bearing walls. And the whole printing process, everything you see here, was done in 100 printing hours. Means that 50 printing hours, we took 50 printing hours for the ground floor and 50 for the upper floor. The 50 hours for the ground floor were splitted along 4 weeks. It took a long time to develop this whole printing process, to optimize it. So there were a lot of lessons to learn in that time, the first 4 weeks. But we were able to optimize the process for the upper floor, and to realize the upper floor in 6 days, only 6 days, with this 50 printing hours. The whole construction time took 8 months for that building, so that's construction time for usual building. And if you consider that's a complete new construction type, that's extremely fast at that moment. So we are sure and we are convinced that we are able to reduce the whole construction time of the building to 5 months, up to 5 months. What are the advantages? The advantages is that what's visible is the design freedom for architects, design freedom for the clients. It's short construction times, it's less manpower for the whole process. You only need 2 to 3 people for that job site, for the printing process itself. And you are able to save costs, because you eliminate some of the other trades, like plastering, like raw material, raw electrical installations, because you're doing these trades in that time when the printer is printing the building. Here are some impressions from the finished building in Beckham. As you can see, the whole structure has been left visible, because it was extremely important for us to show the printing process, the construction process. So the walls in the outer side and in the inner side are completely visible. Yeah, that's how it looks like. That's it. Thank you very, very much for the attention.
Hi, thank you very much for your presentation. I have one question. This is a first of a kind in Germany, this house. And I think you will do some follow-up models of it. How far are you with the legal aspects of DEBT? Is there only a, sorry for the German, the Zustimmung im Einzelfall, or did you already have the ABG and ABZ for that?
We have only got this Zustimmung im Einzelfall. It's permission only for that project, for that construction type, for that material. So if you change the material or the construction type of that building, you have to get a new permission for that.
Okay, but
So there's no DBT, there's no DIN norm at that moment. And I think that's very far away at that moment.
Okay, so that would have been my next question. When will there be something like that? Okay, thank you.
You're welcome.
Thank you very much, Valdemar.
You're welcome.
I'm sure you'll have many more questions, but we're a little time constrained here.
It's okay.
So I would like now to welcome the two last speakers for our session, Isabel Ochoa and James Clark Hicks. They're both part of the team of Associate Professor David Correa at the University of Waterloo. They both hold a Master of Architecture from the University of Waterloo. They're here to show us their work about 3D printed clay structures. So they've looked into masonry components, into facade systems, into light fixtures, meaning they've explored a range of different scales for clay printing. And they will show how they combine traditional ceramics with the novel potential of 3D printing.
Oh, okay, great. Do you want to take this one? Okay. It's the remote. Okay, hi everyone. Thanks to the organizers for the invitation. It's a pleasure to be here. We're all the way here from Ontario, Canada. And so our presentation is entitled 3DP Ceramic Screens, and we'll go over how we've been leveraging toolpath design to functionally grade material properties across kind of the breadth of our body of research. So as Nadja mentioned, it's worth noting that we're part of a research team at the University of Waterloo School of Architecture, led by Associate Professor David Correa, who started the research program in 2017, and we've been with the team since 2019. And so this is kind of a brief overview of the presentation. So we're going to go through 3 projects. We'll first go through grading light, which operates kind of at a mesoscale of toolpath development. Secondly, we'll look at Hive, which looks at leveraging toolpath design on sort of a macro scale in a 3DP masonry system. And then lastly, we'll just go over some of our teaching as part of the University of Waterloo, as well as the Architectural Association Visiting School. So it's kind of worth noting that kind of the scope of the research really focuses on utilizing functionally graded additive manufacturing at different scales to create apertures that capitalize on the viscoelastic properties of clay. Okay, so to start off with grading light investigates how 3D clay printing can generate materially responsive engagements between ceramics and light. And so the research outputs of this project are essentially a series of stoneware and porcelain screens that vary in brightness and illumination based on how light can be obstructed, reflected, or transmitted across their surfaces. And the piece on the right is the piece downstairs as part of the Beam exhibition. So this research develops a computational methodology for grading brightness and light scattering using toolpath tessellations. So in the building construction industry, we have this kind of preoccupation with regulating wall sections because this really streamlines the fabrication process and it regularizes material performance and reduces costs. And so these sentiments really kind of extend into the world of ceramic craft, which is also something we're very actively participating in. So the more consistent of a wall section you have, the more stable it will be during building, drying, and firing. But what 3DP with clay allows us to do is it allows us to grade complex sectional tessellations that's not really otherwise possible with other traditional methods of ceramic craft, like slip casting, extrusion, throwing, et cetera, et cetera. So in this project, we're specifically working, and it's worth saying across all of our projects, we're looking at working with high-fired ceramics. And so we're working with two materials predominantly, opaque stonewares and translucent porcelains. So the stoneware you can see is obviously opaque, but it has kind of amazing plasticity, and it's really easy to work with during 3D printing. The porcelain, however, is beautiful. It's translucent. It's got kind of this very pristine white color. It's able to transmit light. But it's those very properties that make it really great for working with light that also make it super difficult to work with because they essentially decrease workability. It's also noting that the porcelain is thixotropic, which means you have kind of a limited time of working with it once you kind of start material preparation. There's about a 36-hour window before the material starts to congeal. So it's interesting to note that these two prints were fabricated using the same essentially digital file and digital parameters, but you can see the two very wildly different outputs that are yielded with the two different types of clay. So as we just mentioned, these materials have really different behaviors when working throughout the stages of wet processing, drying, and firing the clay. But to kind of synthesize the work, the scope of grading light focuses on harnessing two types of 3D printed high-fired ceramic traits. And in the porcelain, what we're focusing on is light transmission through the clay body as a function of extrusion variability, and that really means variation in the wall thickness. And then in stoneware, we focus on the direction of incident light through porous multi-layered component sections. So when we're working with many forms of 3D printing, and specifically liquid deposition modeling with clay, the tool mark is kind of always a byproduct of the production process. So designers are working with this technology and addressing the tool path in a number of ways. So the first is it's just really a byproduct of form definition. Sometimes we don't acknowledge the tool path at all, but it's ever present. The second is the tool path as an expression of ornament. And then the third is the tool path as a function of material performance. And that can be anything from thermal performance, structural performance. In our case, we're really preoccupied with this mediation of light. And there can obviously be a lot of overlap between the three. But what we're really interested is in this third category of how the tool path manifests. So the grading light research is sort of categorized into kind of 4 light screen typologies, and they're kind of separated based on the scale of their apertures. So in these prints, how they work is the clay is basically directed into unsupported areas that creates kind of discontinuity and porosity in the wall section. And so to prevent structural collapse, you have to kind of isolate this plastic deformation and porosity and limit it to kind of specific moments within the wall section to make this work. And so this diagram on the screen, it displays the layer by layer deformation of each typology when mapped against the digital toolpath. So you can see the small typology has deformation that operates at the scale of millimeters. The XL is happening over several centimeters. So it yields very, very different light scattering conditions. So in our research, toolpath design is really focused on modulating the behavior of light rather than conceiving of these sort of global geometries. So here, with the 3D print on the right, you can see kind of the high degree of plastic deformation that's taking place during the 3D printing process. And then on the left, what you're seeing is a 3D print kind of being recycled or reconstituted after structural collapse. So we're very occupied with making these things as large as we possibly can, despite the limitations of our tools and our materials. So this picture is a little bit deceiving. This thing is actually probably about 50 centimeters tall. So part of the exciting tension in the project is trying to make these things kind of as porous and as big as possible while avoiding structural collapse. So now we're just going to do like a really quick run through of the four different light screen typologies. So this is a small typology, and it's the only typology out of the four that's non-porous and works with the translucent porcelain. So the light is being mediated through the clay body. So brightness and light scattering in the small typology are primarily regulated by porcelain thickness, and it's achieved using two digital tooling operations. The first is extrusion variability, and the second is using the tool path to create these sort of waves that expand and contract in amplitude to change the distribution of material. So the diagram that you're looking at on the right is basically the digital tool path section, which is indicated by these sort of black dots. And that's overlaid onto basically the section of the physical print. And this sort of really was an effective tool in the research to help us understand the plastic deformation that's taking shape in the wall section. So this diagram, here we can see the relationship between wave amplitude and extrusion variability. So for the medium typology, in this typology, we utilize opaque porcelains and stonewares. And light is actually not passing through the clay body. What's happening here is this is kind of a multi-layered section. So light is actually kind of traveling through the wall section. It's not passing through the material. So the tool path in the medium typology is used to create a wall section that's essentially kind of split into two layers that you can see here. So there's kind of an interior skin and an exterior skin, and the interior skin kind of provides some structural stability, while the exterior skin is what's actually modulating the light. So what's happening here is as the kind of exterior layers pull away from that interior layer, that's what's creating porosity, and it's allowing more light to filter through at the expense of structural stability. So the amount of sag in each aperture has to be pretty carefully controlled in order to prevent structural collapse. So the image that you see here depicts a prototype actually being printed with a different type of clay body called earthenware, but using obviously the medium typology's printing parameters. So because earthenware doesn't really have the same plasticizers or the same viscid, meaning kind of sticky properties as the stoneware, it starts to delaminate. So it's kind of this very behavior that I was just explaining, where the exterior skin is pulling from the interior.
So we'll move on to the large typology here. And the large typology is printed in stoneware, and it's kind of characterized by this directional illumination. So the large typology eliminates kind of glare by directing light downwards through these kind of channels that deform into like overlapping light scoops. It might be the easiest way to describe them. The depth of the light scoop is the thing that starts to grade illumination across these screens. Do we lose battery here? Maybe. There we go. So as with the other typologies, this diagram kind of displays that overlap of the physical print section and the print parameters there, or the toolpath section. The large typology might be the best kind of demonstration of this idea of the toolpath being designed with the intent of deformation into a sectional condition that can grade light. So the toolpath is not optimized, but the kind of reflection in the sag is. And we're always trying to kind of anticipate deformation with each iteration of this work. And there's so many factors that go into it, not just toolpath generation, but humidity, moisture control, saturation, print speed, anything down to like the temperature of the room at the time. Printing this in winter is different than printing it in summer. So it's a very kind of finicky process. The final kind of typology is the XL typology, extra large typology. And it's printed in stoneware, but it shares actually a lot of similarities with the small typology in that it utilizes extrusion variation as well as toolpath variation. So the extrusion variation allows kind of light to reflect off these shelves in the interior through these delaminated layers. As extrusion decreases up the piece, so does kind of this direct deformation. So, I have another one there. So the apertures are designed to kind of deform heavily on the exterior and kind of remain stable on the interior. And these patterns kind of overlap to create two kind of like distinct light shelves in the exterior of the geometry, providing kind of this additional room for sag. The patterns realign on the interior to kind of form a more stable internal wall there. And the relationship between kind of aperture size and brightness in this one is nonlinear. It's too small of an aperture, you don't get enough light. Too big of an aperture, it collapses on itself, you don't get enough light either. So there's a sweet spot in the middle there that starts to grade light. So this kind of research, the prototypes we just showed you represent kind of a stage of a continuously evolving working methodology. And this is a photo from a recent exhibition at the Canadian Clay and Glass Gallery. And the oil lamp, what's on display here, is also just on display there, are kind of the second generation of these light screens. And we're kind of working on the third generation right now. So grading light kind of allowed us to focus on toolpath design in conjunction with kind of ceramic craft. It allowed us to tune material performance to light scattering effects at the scale of like a single print layer. And this kind of sits in contrast with the next project, which utilizes a lot of the same ideals, but on a much kind of different scale, which is Hive. So Hive is a masonry wall comprising of 175 3D printed clay units. And it was designed and developed by Ali Cho, Jim Shee, Megan Taylor, myself, Isabella Choa, and David Cree at the University of Waterloo. So Hive is a traditionally bonded masonry system. The stoneware units in Hive consist of kind of 4 interlocking hexagonal apertures. And the apertures have different degrees of opening and closing based on this kind of global geometry across the wall. So Hive kind of presented us an opportunity to access like kind of the scalability, to assess the scalability and constructability of a lot of working methodologies we developed during grading light. And the final installation of this project is a privacy screen that sits at the Investment Management Corporation of Ontario's head branch. So if you go back 2 slides, here. Here we kind of see like 2 masonry units, and they're like kind of least in most kind of porous states. The installation was conceived as a traditionally bonded masonry system, adhered together with just mortar and grout. So the development of this project involved kind of working between digital and analog models to really assess the feasibility of this and get everybody on board that we can do this. We can create traditionally bonded masonry systems out of 3D printed ceramics. This is just an elevation that kind of illustrates that idea that each one in this kind of grid of 175 is unique, and it has a very unique place. And the whole thing spans 5.5 meters by 2.3 meters. So the commission was initially conceived of as 1,600 masonry units. It formed kind of single apertures. With this kind of this was very inefficient in terms of time and labor when addressing this idea of like a masonry unit as a kind of a 3D printed ceramic kind of fabrication process. So we worked with turning the original intent into a kind of a continuous print path that reduced this very large number of 1,600 units down to a scale that was more feasible, 175, while keeping this kind of same scale and same overall scale of the project. So in order to respond to kind of the dynamic material qualities of clay and formulating suitable mixtures for 3D printing at like such an extensive scale, there was extensive material testing, multiple kind of assemblies and mock-ups required to kind of prove that we could do this to both the kind of all the parties involved, the architect, the client. There was lots of kind of convincing to go on that we could do this. And that was the kind of final proof of concept. So here's a shot of the edge condition that kind of fully illustrates that mortar bonded freestanding wall. And we worked very closely with masons throughout this project to kind of ensure that assembly was as simple as possible. So the last thing we want to touch on is just outputs with a visiting school program and the University of Waterloo School of Architecture. Most of these teaching opportunities have focused on developing masonry facade systems or masonry units because a lot of our funding comes from masonry conglomerates, and they're very preoccupied with this idea of the 3D printed masonry unit or aggregate systems. So student projects from the AAVS kind of, the whole thing was sponsored by Autodesk, and the workshop was supposed to be in person, but shifted to remote learning due to COVID. And as a result, we had to develop kind of a tool for simulating ceramic printing that the students could work on iteratively without kind of actually engaging with the material, which is very difficult. So the Autodesk team worked with us to produce this kind of clay simulator in Bifrost in preparation for this workshop that does kind of a pretty accurate job of describing kind of minute deformation between material layers. And that led to like many questions in this idea of like representation and simulation in the design and fabrication process. So we were able to kind of print all the final iterations of the students' work side by side with these kind of simulations that they did of their physical prints. This work kind of comes from an elective that we assist in teaching that's led by David Correa, material syntax. And we want to always kind of encourage students to find friction in material behavior and applications they find most interesting. So as a result, you have a wide variety of projects that engage with kind of design applications. And if you go to the next one here, to more structural capacities, which is always kind of fun to see. And we're really trying to engage this in a Canadian landscape, which is certainly much smaller than the landscape here. Yeah. So I think the final thing we'll leave you with is a small video, of just kind of some shots of Hive printing and the assembly of the Project Hive.
Thank you.
Thank you. Any questions?
Thank you. Thank you for your presentation. Really nice work that you've been doing. The Autodesk model, the simulation model that you showed, can you slightly talk about this? Because it's simulating already the behavior of the liquid form getting shape, right?
Yes.
And from what I know, it's not a really easy process to model. Usually you use kind of I don't know, we are trying, for instance, to use open foam, but simulating as a mesh. I don't know if you have any data about this or if you can talk slightly about this.
Absolutely. So the model's actually, it only functions at the level of simulating interactions between clay particles. So once you have kind of a moment of deformation and the particles in the model collide, that's when the model essentially stops. So that's really all it's capable of computing. So it's capable of computing sag and kind of mild deformation, but it's not going to simulate structural collapse for you. Okay. So it's not a way of testing structural failure.
They've got, Autodesk has got like a great basis for fluid simulation and other simulation, particle simulation. Clay is none of those. It's like straight down the middle, so it's very difficult to kind of, so the best way I can describe that kind of model is, it's almost like it's not based in any of those simulations that they already have basis for. It's based in something completely different. And the best way I can describe it is almost like a sticky rope that kind of has a kind of a degree of deformation that, engages with a certain kind of layer of deformation. It has the capacity to kind of generate full structural kind of collapse, but in doing so, it's just we found that the computational tool became actually heavier than just working iteratively through material processes. Like that computational tool at a certain point becomes so heavy that it's taking hours to simulate these really kind of complex deformations, and at a certain point you can fire up the printer and print it in 30 minutes and get a lot more kind of feedback. So we decided to kind of, we made that decision to limit it to something that students could get a feedback that generates, so it generates kind of aesthetic deformation in seconds because of that.
Thank you. Just a small question about here, wall. How difficult it was to work with difference in tolerance on blocks?
Quite difficult. So there's a lot of tolerance you can see embedded in the joints. So the joints are quite large compared to a traditional bonded masonry system. So we kind of had to build that in to the tolerances of the whole thing. But the final wall was put together by a professional team of masons. The thing that we created in our studio, we sort of laid every brick lovingly, but there's only so much you can do when you're not an expert in the trade. So to answer your question, there's quite a lot of tolerance built in.
Do you know how much the wall growth after it was assembled?
Oh,
It's actually,
question.
we through extensive like testing, we had a sneaking suspicion that this would be the final, so it's actually pretty accurate to.
Yep.
I don't think there's like much growth in the final iteration there, but yeah. I think the Masons were like we gave them those tolerances. We gave them quite large tolerances. I think they could have pushed it. They could have brought those numbers down, but I think we were better like safe than sorry. We had already kind of like scaled it to a certain kind of mortar joint, and they were happy to do that. So.
Thank you.
Thank you very much. So this concludes our first session, and now just before lunch, I would like to invite the ambassador for from Formnext to the stage. So we'll be there in a minute to talk about the opportunities that might interest quite a few people in this room for further research.
Yep. So I just plugged this in. Can everybody hear me? Yes. Okay. I know I'm in between now and your lunch, but I got a last-minute opportunity to tell my story. So for entrepreneurs amongst you, the unexpected is the opportunity, and maybe for some of you, this will change your life. So I raised my own expectations here. So I'm Frank Mouwen. I have a background from TU Delft. I worked in the construction industry for a long time. Also for a long time, I did deep tech startups in climate tech. And at the moment, I represent the European Innovation Council, which started in earnest last year. So as scientists and you probably are aware of the Horizon program, which is the 95 billion, I'm going to read my own slides here, huge program in EU. What I'm going to talk about is a small little box there on the right-hand side, European Innovation Council. Because when we started last year, Ursula von der Leyen, she opened the European Innovation Council saying, we Europeans are excellent in making science with money, but we are not so good in making money out of science, which is a paradox. And the new European Innovation Council is there to help resolve this paradox. I'm going to tell you in the next couple of minutes what the EIC does and what we, in particular for the architecture, engineering, and construction field, can mean for you. So we built the bridge between science and wider market adoption, which is really the chasm, the valley of death. But there's not only one valley of death, there are several valleys of death. We are bridging the first valley of death between science and your first steps as a startup company. Now, just in a couple of bullet points, I can't avoid it, but in short, it is a 10 billion euro commitment by the European Commission to help startups from science to their first steps. It is focused on deep tech, so we don't support apps that deliver bananas within 10 minutes. We support science and adoption into startups, deep tech, science-based startups. There is an EIC fund. I will tell you a little bit more about it later. In short, it's the largest venture capital fund in Europe as we speak. It's innovator-centric. We do proactive management. I will tell a little bit more about that later. And we connect to the innovation ecosystem, which is already there in the various aspects. So again, we make a bridge. It's basically the bridge from an entrepreneurial perspective between the what and the why. A lot of focus is in science on the what, but the first question you have to ask yourself as an entrepreneur is, why am I doing this? What customer can I serve? And what question do I need to answer for him or her? So between research and commercial, we defined three slots, three program elements, which is called Pathfinder, Transition, and Accelerator, with increasing readiness levels of technology, TRL, you probably know it, and commercial readiness level. And they should be in balance with each other. So not go from TRL 1 to 9 and then wonder what customer will be interested. But along the journey, we would like to see a balance between entrepreneurial development and technology readiness levels. I think the battery is low. Next slide, please. So the proactive management is really not only providing you with money, but all kinds of access, for example, to other entrepreneurs, to mentorships, to ecosystems, to trainings, workshops. We really try to help you and support you make your entrepreneurial journey successful. So as an entrepreneur myself, I know it's a brutally hard journey. It really only starts when you have an idea. So there's a lot of help available, and you know, we try to help you do that. An important element of it is that EIC decided to have a small office of program managers. I'm one of them. I'm for the AEC, but you see my colleagues are in other fields which are deemed strategic for the European Commission. I think it's good that now EIC since March this year is also a topic of strategic interest. So AEC, if you don't know, is architecture, engineering and construction. So the most important tool I have is that I can design challenges. Every year I have to design a challenge. I will tell a couple of slides, if time allows, about the challenge of next year, because that's very applicable to what you do here. Now, this slide, in a month, I can show you the final slide with all the numbers. The message of this slide is really, there is an EIC work program. We work with a work program every year. This year work program, 2022, was 1.6 billion. So it is divided, allocated to accelerator, transition, and pathfinder. Again, the low TRL, mid TRL, high TRL. And then there's a division in open calls and in challenge calls. Open calls is bottom up. So you have a great breakthrough idea and you would like to start a company and you convince us that this is a great thing to invest in or to grant to. But there is also a top-down approach. That's the challenges approach. This is where we would describe or would like or call in directions we would like to see further development in. So I designed those challenges for AEC, and I do that together with the scientific community, the venture capital community, and the corporate community to really see what is the cutting edge, where would we like to see more development. Now what you see there, P1 to A8, it's going to be next year. It's not publicized yet. In a couple of weeks it will be publicized. Important for you is P2 and A4. Those are the Pathfinder challenges and accelerator challenges. So again, Pathfinder, more science and consortia based, and it's not a startup yet, but you would like to have a startup in a couple of months or years. And A4, it's accelerator. You are a legal entity and there is going to be investment in that entity. Summarized in 2 words, but there's a huge description around it, but it is going to be about digital construction. I will tell you a little bit more about it later. So I also had to convince with my own pitches within the European Commission to 27 member states and all the director generals where we would like to allocate the challenge money to. So this is a couple of slides I took out from my own pitch in the last couple of minutes before your lunch about the challenge, the reasoning behind the challenge. So the EU faces a monumental task to decarbonize within 30 years. We kind of know that because we also put that into law almost by the European Green Deal. But greenhouse gas emissions of the construction sector are still estimated to be 5 to 12% of total. And we can't Tesla that away. We have to do something with our sector. So good progress is already being made with operational greenhouse gas emissions. So this is anything with insulation, double glazing, heat pumps, and everything during the life cycle of the building. But we also see that embodied greenhouse gas emissions increase both relatively and absolutely. So as we improve on operational greenhouse gas emissions, we use materials that have more embodied carbon. So carbon which is emitted during the manufacturing and production of the materials, like cement and concrete. And in relative terms, if you look at the trends development, it's up to 50% of the future building emissions are expected to be embodied. And we have to do something about it. I think Bill Gates mentioned it with his investment fund, we have to build 1 New York City per month for the next 40 years. My belief is if we do it in the same way we have been doing it for the last 100 years, it's not going to end well. So there are 2 important contexts for us, in a European context, we have the European Green Deal, which basically states net zero by 2050 and the roadmaps toward that. We also have, from a customer perspective, because Ursula von der Leyen thought that the Green Deal was a bit too technocratic, we have the new European Bauhaus for our sector, which basically lays out the vision for sustainability, togetherness, and beautifulness. So which is, I think, a great tool for us to guide our efforts. Now, I would like to talk about one paradigm. If you look at nature, I think in this conference, this is really spot on, because nature uses very few materials in endless complex ways, and humans use very little materials in wasteful, simplistic ways. So if you look at a butterfly, zoom into the wing, you see gyroid structures. You also see the gyroid structures being printed with all those printers here at Formnext. And if you contrast that with the way we use formwork to pour concrete, I think we have some opportunity directions to go. And in my view, the key to the door opening is a deep digitalization of our sector. We also have an historical dimension. So we started with unreinforced concrete 3D. On the left-hand side, the Pantheon in Rome, still the largest unreinforced structure in the world, I believe. Then we had a long period of stereotomy, where the stonemason and the constructor worked very intrinsically together and made beautiful eggshell thin constructions. Then we had a period of where we had fossil fuels and abundant concrete materials. And I think the logical next step is going to be a digitalized computational design, digital fabrication, and new materials. One more slide. Because as it will be shown in the work program for next year, you would be curious and interested to learn that what we would like to see is proposals in the area of computational design, alternative materials, and digital fabrication. Thank you very much.
Before you get your lunch, I wanted, he found us some 2 weeks ago, and we got a chat, and he wanted visibility. This is the person with the money. That's super important.
It's your money, by the way.
Yes, it's our money, but he's the one making the outline of EOC grants. Super prominent research grants. You have to apply for one. You have to apply for one. Valentin, you have to apply for one. There's Alex. You. This is the moment to get a business card. He's the person sketching what's going to happen next year. This is the perfect moment. And that's why I wanted him to present here. Thank you.
Thank you for the opportunity.
Thank you.
Thank you. That's good.
Kick off, Philip. Yeah.
Okay.
Should I?
Yeah,
Okay.
no,
So
yeah, I'm only leaving tomorrow. Yeah, just
I
find a flight
welcome everyone back
today to arrive
from lunch.
4th of,
Or if your
this evening.
experience was like
Sorry.
mine, it was back
talk
from
later.
watching
It's
a
a nice
very long
presentation.
queue of people queuing for lunch. Welcome back to session 2. My name is Paul Nicholas. I'm an associate professor at CETA, which is the Center for Information Technology in Architecture at the Royal Danish Academy in Copenhagen. The format of this session is that we will have 4 speakers. We will have a split in the middle after the second speaker for a 10-minute coffee break. And again, the speaking each presentation is 15 minutes with a 5-minute question session directly afterwards. So before we plunge into the speaker presentations, I was invited to share a little bit about what we are doing at CETA at the moment, some of the research that we're doing, and I would like to do that. So I'm going to show a couple of projects. I'm going to, maybe with a clicker, that would be easier. Show a few of the projects, but also before plunging into that research, maybe just preface it with a little bit of the underlying motivation and research thinking. So you're all, of course, aware that we are living in and working in and researching in a time of climatic and resource crisis. And a significant component of that is our building culture, and particularly the way that it has intensified around a particular number of materials, accelerated around those materials, and also has maybe developed into quite linear material flows. We're often presented with this perspective from the global construction industry perspective or the European constructive industry perspective. But I think it's also important to understand that there is a sort of on the scale of the individual, there is also an impact, quite a significant impact of this crisis. And that is individually, what are the material resources and choices that are available to us to specify, but also to inhabit in the buildings that we occupy. So in response to this crisis, many industries are engaged in quite a fundamental shift of some of their underlying perspectives. This is the electricity industry in Denmark, and you can see actually that in a very short time, there has been a radical change in the underlying construction of that industry. And within architecture, of course, we are engaged in a similar transition. And what's interesting at the moment is I think that we can define different research trajectories, different ways that we are thinking about as a means to meet this crisis. One of those is optimization, and the idea that we can look to optimization, the paradigms of Industry 4.0, smart sensing as a way to build smarter with less materials. A second trajectory is perhaps the idea that we might be able to grow it all and look to biogenic materials, look to bioengineering, and think about how these materials can be a sort of new material basis for architecture. Understanding that the world has a sort of photosynthetic ceiling, of course. A third trajectory is then to look to pursue reuse and recycling, and the idea that we might be able to connect our production of new buildings, new interiors, with anthropogenic material resources which are already out in the world. So at CETA, we, and I think a lot of the rest of the world of architectural research have argued that optimization has been, I think, the most sort of productive research pathway, and that if we are able to connect smart nodes of design, smart materialization and fabrication and assembly processes, that we will be able to reduce our material impact on the planet. But I think for maybe over the last years, we have been, in our research, questioning that assumption and looking more towards the idea of the biosphere and biomaterials as a place to put design and research emphasis. And here, thinking about that not as a sort of total solution to the problem. It's obvious that all three of these trajectories will need to be part of design practice, architectural and engineering design practice as we go forwards. But because biomaterials and a biodesign practice lets a different or another perspective emerge onto our practices of simulation, digitization, and additive manufacture. So some of the materials that we have been working with, these are a selection. They are all materials which are waste stream materials coming from agricultural waste streams from the timber industry, from the paper industry, from agricultural fields, also things like seagrass. We treat these as a material system, so we're able to exchange these materials within a recipe and produce materials that have quite different properties, quite different aesthetics, different expressions on the basis of their constituent ingredients. Here you see the blue materials here come from cloth and cotton, recycled shirts. Some of the browner ones are coming from bark, which gets stripped off the trees at timber mills. What we are then interested in is how do we start to work with those materials and put them together within large-scale printed elements. So to look at the opportunities for grading and very localized specific material properties and to connect them with possibilities in additive manufacture for making architectural elements. And a lot of that work is also then about addressing the issues of scaling up. So scaling up through robotic printing, scaling up through looking to gantry printing with our partners Cobod in Copenhagen. Also looking to see how can we use robust technologies that are being deployed at building scale, and start to use them as enablers for new materials, for example, other than concrete. Another part of scaling is the idea of scaling material quantities. So also thinking about how do we produce printable materials easily, cheaply, and efficiently, ideally on site, ideally using material constituents that are local to that site. And how can we also scale up by understanding that perhaps we are not building buildings that are entirely 3D printed, but we are making elements that need to engage with the richness of construction industry, which means that they might need to engage with hand practices, with other kinds of scanning practices, or other material and building cultures. So some of the building elements that we have been printing are reaching at the moment a scale of 2.5 meters by 1 meter, and maybe a weight of 60 or 70 kilograms for some of them. And we are, and as I think an interesting part of this is also sort of understanding from a design perspective that some of the geometric logics that we are working with in the design of these panels are not so much based on logics of optimization or structural optimization, which is where we have looked a lot in the past for additive manufacture, but they're based on the logics of evaporation, actually, and of maximizing air surface so that we can control and speed the curing of some of these materials. So you see here the challenge. We are printing with slurries. They contain a lot of water. That water needs to evaporate out, and there is a lot of dimensional change, or there can be, in the materials. And here we are working with using sensing and also modeling procedures to be able to track that change and to predict it. So building databases that we can then link to machine learning based models that are able to predict eventual forms. Here you see some of the monitoring setups. We're using internal monitoring, but also external scanning and point positional tracking as part of that, and making predictive models. The point of making those predictive models is to have control over the geometry, to know where things will end up, so that we can then begin to also utilize some of the those geometries to make quite precise fitting components and meet issues of tolerance. So some of these are different versions of the same material. This is a slightly heated version here, where we are using seagrass as part of a filler and a fiber in conjunction with some biodegradable binders, and being able to start again to scale up some of our materials and some of these panels to quite large interior installation size. And one of our interests here is to think about these materials not as one-to-one replacements of materials that we have already around us, perhaps in the building industry, but to look at what their particular properties are, what makes them different to other 3D printable materials, and particularly around their ability to modulate internal humidity and modulate internal acoustics within an environment, and to look there in terms of their potential for architectural impact and architectural expression. So that's, I stopped that small insight there, and I just need to get my notes to invite our first speaker to the stage, who is Bruno Figueroa, who is an assistant professor at the School of Architecture, Arts and Design at the University of Minho. He holds a PhD in construction and technology and a master's in modern and contemporary architectural culture. So I invite you to the stage, Bruno.
Thank you. Good afternoon, everyone. Paul, thank you for your brief introduction and for your presentation from your work at CITA. It's a great pleasure to be here today. I want to acknowledge the effort and the work from Philip, Jonas, Oliver, Bastian, and Ulrich, and of course for inviting me to present here some of our work. The work that I'm presenting here today is mainly focused on additive manufacturing of natural materials, namely biopolymers and fibers for the production of building components. This work belongs to the research, ongoing research of the Tiana campus at our lab, Advanced Ceramic Laboratory at the University of Minho, under my supervision and of Professor Paulo Cruz. Just to give a brief context of our work, I would say since 2016 we start a first set of tests in ceramic materials, starting from small specimens. We moved to building parts, trying to propose new infrastructural roles for those components, but also to explore new aesthetical possibilities. Here we can see a set of prototypes of staves for multifunctional columns, a work developed by another PhD candidate, João Carvalho, and also a beam with a hybrid functionality, with a hybrid system, mixing ceramic blocks with timber elements. More recently, we start to scale up and start to explore 3D printing of concrete-based mortars with the goal, of course, of providing a more sustainable approach on the use of cement in the construction industry, cement and compositions of cement with other natural materials. We are looking for the implementation of something, let's say, similar to what Paul was presenting, computer vision to the control of the flow, but also to build a database for machine learning to control the behavior of the mixes while we are printing. In parallel, we are developing a computational design framework for design and production of custom building blocks for waterfront barriers and piers. Even if the approach could be seasonal, we believe that it can bring big value for those public spaces, and this is something that we are working now. We are starting by doing photogrammetric surveys and custom design our 3D printing elements and blocks for those public spaces. We also have been working, and this a previous work that is being shown here on the exhibition on the VM trade show, and it results from the initial research from Tatiana on the use of biopolymers and natural fibers, trying to integrate it in additive manufacturing processes. This so it's the work from, say, 2 years, 3 years ago. And as a proof of concept, we manufactured a wall made of blocks with 3 types of materials or mixtures. The upper part, we are using only cellulose-based mixture with starch. The second row of blocks, we mix the cellulose with sawdust regarding the waste from wood material. And the bottom, we try to mix the cellulose starch with the clay. And despite the lamination of the blocks made only with starch and cellulose, the test shown that the ability of printing, 3D printing with these materials is quite achievable. By adding also a small amount of cellulose to the fibers, to clay, we also noticed that there are less deformation of these pieces when they are drying and fired, if compared to pieces that we were only printing with the clay. So, okay, wrong button. Going back to biotiles research, it departs from the notion that we need to improve the management of marine resources and to reduce the waste of fishing industry, which is largely made by biopolymer materials. Seafood shells, fish scales, squid skins, and fungal cells are rich in chitin. And chitin is a monomer material, structurally similar to cellulose, that can be obtained from these waste, from the waste of these materials. And chitosan is a polymer that derives from chitin. Considering this, our aim on this specific research was to start testing materials based on biopolymers such as chitosan, starch, and mixing with cellulose fibers. We know that chitosan would introduce some plasticity, the starch would help on the aggregation of the mixtures, and cellulose fibers introduce some resistances. Finally, we are using liquid glycerin to give some flexibility to the composites. Here, just a set of material samples made and tested with the different percentages of raw material. This helped us to, of course, have a visual analysis of their behavior, either the color, either their textures, and helped us to move on and to start to decide which mixture we'll be working on. Here on this last group, we basically were selecting mixture that with more amount of starch and less amount of chitosan, because we achieved good color, good transparency, and also the fluidity of the mixture that will allow us to print or extrude to the printed extruder. If compared with the behavior of, for instance, of the group 2, with higher amount of chitosan, it gets too hard to start printing and even to pour in a mold as a manufacturing processes. So then we start doing first set of tests. We start for defining grids and trying different mixtures based on chitosan, starch, and glycerin. Basically, the main goal was to start to verify the behavior of the material. We also noticed that, of course, we were printing on those samples. We're printing on a flat surface, and if we move that a fresh printed specimen to a kind of a mold, it will adapt, and after drying process, it will assume that shape. A second set of tests were done. Here we show 2 grids. Here we were printing 4 layers for each one of those specimens, and we're using again different amounts of chitosan and glycerin. And it's possible to understand that the more chitosan, the more rigid and dark material gets. And also, we see that on the left read, higher percentage of glycerin has a better plastic behavior. When a force is applied on surface, it changes its shape, but it doesn't. The left doesn't recover it, while the right one, with the lower percentage of glycerin and higher percentage of ketosane, more rigid, it deforms, but gets to the initial shape or recover almost the initial shape. So it's a kind of shape memory effect that you will find on that composition. So we're deciding to mix these two both materials, a more plastic mixture and a more rigid mixture. One was being used on the base for 3D printing the grid. The grid is the base is a liquid material, doesn't have any celluloses, while the grid had a certain amount of celluloses in order to provide more resistance to the composition of the material. This is just an image of one of the first specimens and tests combining these two. We see that both materials fuse slightly after drying, creating this bioplastic membrane. So in order to now entering on idea of the biotiles, we start thinking on this with challenges of bringing here a prototype to the exhibition, and so we understood that we should try to take advantage and combination of these materials, and trying to develop a construction system. So basically, we get this idea of reinterpretation of the cladding with thin slate panels that we find in many historical buildings, also in porcelain Guimarães. We have this composition similar to fishing scale superimposition. And so to achieve the overall shape would be really easy by defining specific molds and pouring the liquid material. Then we were using reinforcing the membrane with this structure. We thought also we're crossing here the inspiration of using veins of plant leaves with the aim of acting as a structural reinforcement. The prototype was supposed to have 35 tiles with different shades and textures, and we started producing these. So we made previous testings in July that worked pretty well, and this image is from October when we start doing the final prototype. And you see here the base with liquid mixture, and then printing the base, the fibrous mixture with the cellulose above it. And eventually, when all stages are completely successfully, the membrane looks homogeneous and semi-transparent. Actually, I brought a few samples that I'm leaving here. If you guys want to look at during the break, please do it. And so we have this homogeneous look and with semi-transparency, and the printed areas with the granular finishing.
And our idea here in Darmstadt is to print such a 3D structure on a flat glass, on a semi-finished product, and to create new glass joinings, glass joinings, such a point fixing here you can see in the facade, or some reinforcement on flat glass. And so we can create some advantages, like we can create a homogeneous geometry and the connection in a desired geometry for some individual products. And so we can increase also the transparency in the facade, and we can stiffen it. And you have also the possibility to reduce the plastics inside, because plastics are not so good because of UV, long lifetime of some facades. Here we have the problem of aging. And so we can avoid this, and we can create from a boring 2D structure, 2D structure, 3D structure, and also as a colored structure. And so we can bring with the technology additive manufacturing, we can bring the function and the design together to create such new products you can see here. There are different methods more or less available. I think you are very familiar with these methods, but it's not all possible to print glass. There are fused deposition modeling on the one side. There are some research groups, Micron 3DB and Swarovski. There's an action also the MIT and QCell, and they use this technology to print such structures, but it's more or less for interior stuff, like arts, for example. And there's a group in former times at the KIT, now it's in University of Freiburg, and the startup Glasomer, and also the ETH Zurich, they developed out of stereolithography a possibility to print 3D structures out of glass, very thin, very tiny. They used here quartz glass. It's very expensive to do this, and they can create very cool structures, but it's not possible to use this for the built environment because they are too tiny and the technology is limited. Here you can see an overview. I don't want to get too much in it of the different technologies which are more or less available for 3D printing of glass, and what are the possibilities and the pros and the cons to this. And if we print with fused deposition modeling, yes, we will create a rough structure at the surface. This is a disadvantage, but we don't need really a pre-finishing, and we can create very fast, very big structures. If we look to other processes, so we can create with stereolithographies also not so rough surfaces, very cool one, but we had a lot of problems with the shrinkage because of the debinder ring. And this makes it very difficult and challenging. Okay, let's talk about the constraints and what we have to think, or what we have to recognize if we use glass as a structural material. On the one side, glass is very strong. If you look to the compression, we are here in a range of 1,000 Newton per square millimeter in the compression strength. But you know it, glass is brittle, and the flaws are critical on the surface. And if you bring tension on it, or like bending, it's not so good. We are here in a range of 15 Newton per square millimeter. This is a factor of 20. There's a difference in this material. Then we had also the problem during the production, residual stress. Here you can see it with polarized lights. You can see here the colors. There's residual stress, and it's not controlled. You will see a crack if the residual stress is too much during the production process. And sometimes it's not possible to anneal the things, and if the structures are too big, like this cube here, it's more or less 1 meter by 1 meter by 1 meter. They use, or you need a lot of time for a annealing process, and if this not good managed, you will see here some cracks, and this is not so cool if you think of an overhead glazing. So let's talk about the temperatures. We are in a range of over 1,000 degrees for our production, not like plastics. Here we are in a range of 200, 300 degrees. And here you can see a diagram viscosity against the temperature for different types of glass. We want to deal with the soda lime glass, the normal window glass here, and we are here in a range for our production to join the glass together of the flat glass in a range of 820 to 1030 degrees. And if you look to quartz glass, here in a range above 2000 degrees, so it makes no sense for us. And on the one side, we need temperature to bring the things together here for a joining process to transfer the loads. On the other side, if the temperature is too long, too high, we will create a not so cool structure. We will create a 3D structure, and if it's too hot and too long, too hot, we create also from the 3D structure a 2D structure. And so this is a challenging effect. Here you can see on the left, on this side, a very line on the flat glass, 3D printed. It looks very well, but if you look in detail here, the connection area is very tiny, so you can't transfer no loads. If you look to this sample, it looks not so nice, but the connection area is much bigger and you can transfer some loads. This is a challenging factor. And if you look to the strengths, on the next slides you will see a cross-section out of such a sample. Here you see the glass base plate, and here a colored glass rod, and here the interface of both. And here you see the scale, and you see, okay, there's more or less, or there's no gap between. Also here you can transfer loads, and we carry out an indentation test with a Vickers diamond, and there we create some cracks, and the crack goes through this interface here, and so you see, okay, here we can transfer loads. It's a homogeneous connection. This is the other sample. Here you can see we did the same. Here you see really a gap. Here you see the indentation points or dots, and here we create also in this area a lot of damage. So it's not useful to transfer the loads. And to bring this in a process, it's challenging. There's a big team behind me to do this. We need such a chamber because we can't print on normal air temperature. We needed a chamber in a range of 500 degrees. We had the kiln to use also waste glass, heated up in a range of 1,300 degrees. Okay, thanks. And bring it out in this chamber with a heated nozzle, and so we can create such a structure. And we use a special torch to this for the connection of the joining area. This is our machine. It's a prototype. Now we had some challenges with one furnace, so it stops now a little bit, and we hope next month we can work harder on this topic. And we look also, if you print some samples, to the safety conditions for the civil engineering. Here we speak about lamination processes and also pre-stressing of such samples. Lamination process, we did this with such a 3D printed structure. We laminated this here together. It's a work of Amir and the LZH Hannover. Here bring it together in a dimension of 500 by 500 millimeter. Last year you can see it was also here at the beam, and this is possible with our machinery. Okay, with this technique we can create such new glass joints. You can see here you see the conventional stuff with adhesive, with borehole in such a brittle material is not the best idea, I would say. So we can create such a structure with the 3D printer and mount here such a point fixing, and it helps us to avoid boreholes in the facade. And here you can see the structure from last year we presented here. This is in general possible to do so. The other thing is for reinforcement. If you look at glass is driven, large glass samples in the window are driven more or less by the deflection. Glass is, because it's thin and the bending behavior with a thin structure, you can see this. And if you fold this paper and print some, for example, some ribs on it, you know what happens. You can stiffen, and so the structure, and so you can stiffen like such a cross here on such a plate. Here's the cross section, or in this direction. Here it's also created with some molds and other possibilities for design aspects. You can create such a structure and stiffen. You can reduce also here the weight and also the footprint to this. And at the end, you can create also such sandwich panel with 3D printing with such a lattice structure. This is also in general possible to do so, and also for some linear bearing in the facade. Here are some samples. Some samples are also here. What we create, it's a feasibility study. We bring some ribs on it to stiffen it. And so we can, for example, we can reduce here the weight of such a sample. If we had a span length of 2 meters of such a glass plate and a surface load of 1 meter and with a width of 1 meter, we need 12 millimeter, more than 12 millimeter for the criteria of deflection thick glass. And if we bring on 6 millimeters thick glass, 6 ribs in the dimensions of 40 by 10 millimeters, so we can reduce the weight more or less than 40%. And if we increase here these values, we can reduce more. Also here we have the possibility also for sustainable issues. I want to sum up. It's challenging because of the brittle material behavior, the residual stress, and the high temperature, but it's feasible. And now the next step is we want to print on larger structures in the dimensions with the new 3D printer of 500 by 1 meter. And our vision is to print in the dimensions of such a flat glass of 3.25 meter by 20 meter. This is our vision, not tomorrow, but in the next years. And so we can use also waste material. We can drink a beer today and throw it then in the printer, and we can create a structure on it. It's also an issue, also not to drink, also to drink beer, yes, it's also an issue together and have some new ideas to it. And we think also about the safety requirements for the building environment. This is also very important for us to bring it in the structure, not only in the living room. And we can bring also new functions to it, design, color, and also light aspects. And so we can create such samples. And so in the end, we bring with AM also for the other materials the function and the design together and create new stuff. Thank you for your attention. I hope you can enjoy. And if you have questions and demands, please ask me. Thanks.
Questions? Volunteers? I have a question, maybe to start with, Matthias. Thank you so much for that presentation. It's really amazing to see. And maybe I'm remembering that maybe when it is molten or hot, glass wants to have a specific thickness. It wants to be about 6 mil thick. Mm-hmm. And I'm wondering, does 3D printing give you a way to move around that, to have thicker sections, for example, or thicker thickness? Or are those kind of other, the other sort of learnings from other glass practices, are they something that you're able to bring in to the digital manufacturing process of glass?
Yes, we have worked here also with some guys from glass manufacturing. Glass maker, they mold glass for their knowledge. It's very important, and also bring also the guys from the handmade process together with the guys from the informatic for the digital things, to bring all two disciplines together to create new structures. And this is really important, and not to do this by our own. It's not possible for me, as I'm only a civil engineer, to create such a work alone.
Yeah. It's also interesting what knowledge can be transferred from a crafts practice to a fully mechanized practice, so, or one particular technology.
Mm-hmm. Yeah, it's also especially we had a gap in the future for the workers, and so this is really a problem in the industry, especially in Germany. I don't know in other countries. I think the same. And so we can use such digital machines to create such structures and not handmade one, because we had no workers to do this.
Yes.
I'm not a little expert, but in one of your slides, I believe it was 13, you showed me this, this ribbed concrete floor slab, which is the design principle being only compression only, right?
No, it's a plate. This is a plate. It's for bending stuff.
Okay. Well, I think in Zurich they make these plates which are compression only. I'm always fascinated by this 1000 megapascal compressive strength of glass. Do you envision glass being more widely adopted as a structural building material? Or?
Nowadays is structural material, but if you look to the glass facade on slide number 3 or so, to the Chanel, it works as a structural material. And yes, we have to optimize the structures. We have to avoid bending, more or less, to come, you mentioned, to the such arcs, for example, to use this, and so we can activate the compression strength and avoid the tension. And this is a good idea, yes, and for optimization process. Also, we have to do this.
One last question.
Thank you very much, Matthias. Very nice presentation, very interesting. I think the safety issue is something indeed that is difficult to solve, but I'm curious how you will do that. My question is actually, do you also envision printing of glass for repair rather than reinforcement, but if you have a damaged panel or...
In general, I would say at the moment, it's not possible because in practical, you can't go in the facade and print because you have to heat it up. If you have quartz glass, yes, it's possible, but not with soda lime glass because of the temperature differences, and then you will see the cracks.
But if you're able to take it off the facade, I mean, so
yeah, yes,
reuse and.
This is, but you have to bring a temperature on it, and this makes it very difficult because we are here in a range of 500 degrees for the rest of the sample to the joining area. Also this, I think, now I would say no, but we can think together to this topic.
Okay, thanks.
Thank you very much. Maybe we have a 5-minute break and come back.
Danke für die Samples.
Gestern gesagt über die, dass es so leise ist, das haben wir mal an den Ton weil es ein bisschen Rückkopplung macht. Wir können das mal probieren, dass wir den Ton
Oh, that's okay. Yeah.
Okay, so I'll introduce our next speaker, Susie Payne. Susie is an architect. She's a PhD fellow at the Royal Danish Academy in Copenhagen, Denmark, and her research explores 3D printed ceramics and the ornamental and tectonical strategies to use them for cladding systems. Susie.
Yeah. Thank you so much, Paul, for the kind introduction, and thank you so much for the Beam team for inviting me to be here. It's really a privilege and a great honor to be able to be part of this really exciting conversation about additive manufacturing in the built environment. So today I'm going to talk about clay. I'm going to talk about 3D printed ceramics as an architectural material, as a cladding material, in this talk which is called How to Dress a Column. So I'm going to tell you about this project, Textile Column. It's a 3D printed ceramic interlocking tile system, which is a contemporary prototype for additive manufactured ceramics as a fire-resistant cladding material for structural steel. So I'm going to talk about the making of it, but also the background to making it, which is actually really an illustration of my approach to working with 3D printed clay as an architect. And I would say this is approach is something that's informed by craft, the history of shaping clay as an architectural material, and more theoretical ideas about dressing structure and metaphorical references to textiles. And I'll finish just showing you a couple more projects and collaborations from my PhD research. Now this is a diagram that aims to contextualize what I talk about, what I do. So I work in the field of clay printing, which is of course part of the larger field of additive manufacturing. But this has very interesting crossovers and intersections with architecture in the form of tiles, bricks, and cladding systems, but also the field of digital craft-based ceramics. So we're thinking crafts, vessels, and much smaller scale items, more at the scale of the applied arts. So there's obviously a very technical discourse that happens here that links all of these fields because we're pretty much all using the same types of systems and machinery. But there's also a more theoretical discourse that I'm interested in, which is more part of the field of architecture, which is about ornamentation, how we actually design and make ornaments, what they actually mean. But also the field of tectonics, the science, the art of how we put things together and design joints in architectural systems. So in the run-up to Textile column, what I'm going to do is I'm going to show you 4 projects that really have informed this approach. So this story starts with really the history of clay as an architectural material. In 1871, there was a big fire in Chicago, and what architects and engineers noticed was that the iron-framed buildings or the iron-frame facades, they weren't actually destroyed by fire because the ceramic was acting as was protecting the iron frames from the fire, because, you know, as we know, at a certain temperature, there's a catastrophic collapse when we're using metal as a structural material. So Louis Sullivan and other architects of the Chicago school adopted the use of terracotta to create these fantastic ornate facades for the steel frame buildings. And this is a really beautiful use of the material because it's functional, obviously, in the sense that it's protecting the steel, but it's also incredibly decorative as well. What we also see in Sullivan's facade is a very clear reference to carpet patterns. This is an Assyrian carpet pattern on the right-hand side. And we know that Sullivan was very inspired by the writings of the theorist and architect Gottfried Semper and his Bekleidungsprinzip, or theory of dressing, and the idea that the expression of architectural walls is something that's derived from textiles. So Semper's theory was that textiles were one of the first architectural materials in the form of primitive tents and these kind of first enclosures. And he believes that all subsequent walls express this textile origin through patterns and motifs originally related to fabrics and carpets. And this is exactly what Sullivan is trying to do here in terracotta. And the reason this is important is that this metaphor is driving the artistic articulation of the material as it performs its functional role in protecting the steel. So we take a little diversion away from ceramics here to concrete. So this is Frank Lloyd Wright's Millard House, built in 1923 in Pasadena in California. And the reason this is important is, well, one, it takes the textile reference a step further. So it's worth pointing out that actually Frank Lloyd Wright was the apprentice of Sullivan, so this discussion about tectonics and textiles was something that must have been happening in the spaces where they were together. So in Sullivan's building, this textile reference is something that's really only skin deep. The textile references are on the surface. But for Frank Lloyd Wright, he's actually taking this to a more tectonic level and actually weaving the structures together with the metal rods within the frame. So it's tectonic. The textile reference is something that's tectonic rather than ornamental. So coming back to ceramics and fire-resistant cladding for steel, the approach that Sullivan and the other architects of the Chicago school, it didn't stay around for very long because engineers got much better at protecting structural steel through the use of intumescent plates and other cladding systems. So we only really see these buildings built for a period of around 30 years. But I put the wrong date. In 2002, the French practice Lacaton Vassal, they made this really very beautiful porcelain cladding system for structural steel. So the idea, it's very thin, they're only about 5 millimeters thick, but the idea is this kind of very thin veil-like ceramic cladding will protect the steel in the case of fire. Unfortunately, this didn't go into production as they had planned because they weren't able to really solve the joints between the individual pieces to make it actually work. And also there were issues with how you would actually adhere these tiles to the steel structure. So this is where we come to additive manufacturing. and additive manufacturing ceramics. And one of the most exciting things about additive manufacture with ceramics is this very precise deposition of the material, which means we have much more control over the geometry and the design of the pieces. And we can think about using additive manufacturing to really design really innovative joints between things. And this is where I show a couple of Bruno's work from Bruno's laboratory, the Advanced Ceramics Lab in Guimarães, that show ceramic, discrete printed ceramic elements that are joined together in an innovative way. So the one on the right-hand side, this is the use of magnets, and you can see where they've controlled the print path to mean that you can actually place the magnet within the element and join them together. And on the left side, this is their Fiscus Columns project, where they made these bespoke plug systems that actually deal with the issue of the joint in the 3D printed ceramic piece. Now you'll see with a lot of additive manufactured products, there's this promise of continuity. You can keep printing and printing. But this is not the case in ceramics, because with ceramics you have to fire it and you have to dry it. So when you print something big, it's going to deform. So really in this field, we do really have to think about how how pieces are actually joined together. And this is a classic architectural problem. So now I'll talk about the textile column. And what I want to say is the 4 projects I've just shown you, they set up a series of questions. So can ceramics be considered again as a decorative fire-resistant skin when using additive manufacturing? How do you deal with the joints in such a system? And what happens... Sorry, I've lost myself here. And what happens when you consider historic textile references as either ornamental or tectonic strategies? So obviously with the aesthetics of additive manufacturing, there's this quite obvious weaving or knitting-like effect. And I'm interested in taking this textile metaphor something a bit further than just being a surface condition. So how do we actually interlock and think about how we can actually join the pieces together, thinking about textiles and fabrics as folding and interlocking and woven together pieces. So this piece here, this is one of the earlier tests I made thinking about making these joints between pieces. And I'm also thinking about how this joint can actually be something of an expressive seam to actually really make a statement about the point where 2 things are joined together. And these pieces are made in a way, so these are pieces from the actual column, that they're printed together, so but they only very lightly touch each other. So if you look at the print paths, there's 2 things happening here. The inner and outer layers, they're actually fused together, so you can't actually take them apart. But the adjacent pieces are printed at such a position that you print them together and they're very lightly fused together, but as the ceramics dries and it becomes leather hard, which is something after about 24 hours, you can actually take the pieces apart and gently crack them, and then when you like this, and then you can reassemble them and put them into the kiln, fire them together, so when you've actually got them as your final element, they're actually a very good fit, and you get a really good fit around the steel. So here, this is the system itself. So you lock the piece around the column, you add the adjacent piece, and I'm using here just a steel tie to tie it together, which is also kind of in the theme of weaving and knitting them together. But the joint's actually hidden as the corresponding piece then comes over the top. And the idea is that you could just go on and on like this. It's supposed to be a dry fixing, so the idea is that you could disassemble it at some point if you needed to. But the reality is, as I've been putting them together, they do actually need a bit of adhesive to hold them in place. But I think this is the point to say that this system is not perfect, and this is where a lot of the work that I do sits. They are ideas. They're kind of pre-prototypes that explore theoretical ideas and practical ideas that have the potential to perhaps be taken further. Now, that's the final column. You can see it downstairs. It's somewhere in room 11. And the outlooks really for this project are working with an inner and outer layer and parametricizing the layers. And you can obviously think about working with different profiles of steel. I think there's potential in ways to think about the reinforcement. You could use the interstitial areas to think of other ways to actually weave and tie the pieces together. And of course, this interlocking principle can be developed with clay at a bigger scale or even a smaller scale as something that's both functional and ornamental. So a question I get asked quite a lot is sort of like, so what? Why do we need any of this? You know, you can quite easily pull apart the idea for ceramics as a, you know, ornamental ceramics as a skin for structural steel, because there's other ways to do it. But I think this project and this approach actually opens up many more questions about how we work with additive manufacturing in clay. So when it comes to structure, more artistic questions about what's concealed, what is revealed, what is ambiguous and what is clear. And of course, how joints are articulated when working with additive manufactured clay. And I think there's also some architectural questions which are technical, but also about art and beauty, which is something that, of course, Sullivan and Frankfurt both address in their approach. I've got a couple of minutes left, so I'll just tell you about a couple of other projects. This is an ornamented column. It's also sitting downstairs. This was one of the first projects I did as part of my PhD project. And this was about thinking about the language of 3D printed clay. And so I knew I wanted to, and it's this ornamented column, and it's on site here just as a kind of experiment for a day. And what I wanted to do was think about the historic architectural languages of the site and think about ways to actually translate them and reinterpret them in clay. So those tiles in the back with these kind of vegetal patterns on them, I registered them and started to think about how I could work with the print paths to express them in the clay. So that's kind of the formal or aesthetic link between the site and the column. And so the idea is to create a kind of symbiosis thinking about the historic architectural languages. And these are the pieces of the column. And as you can see, they're a much more kind of crude form of the textile column. The inner structure, you know, it's the same. It's an inner and an outer structure, a more structural internal core. But these pieces actually act more like blocks, like dry stack blocks, and just use the column as a kind of support in the middle. And in these final couple of slides, I'm going to take a deviation from columns and talk about walls. Now, this is a really beautiful project made by two students from the MASD fab at ETH in Zurich, Joachim Tobar and Muslima Ravikova. And this is a tutoring collaboration between myself and Maria Smigielska, a researcher and architect at DBT. And we asked students to explore the articulation of joints in a porous ceramic screen wall system. And what I think is really beautiful about this project is it's kind of addressing this question about continuity in additive manufacturing, because they're not actually making clear differentiations between the joints. They're actually thinking about a fusion of the elements that interlock together but are also held in place by a bit of mortar. So I'll finish now, and I think what these projects are at least trying to show are an explorative approach or an attitude to joining clay, additive manufactured clay, examples of how thinking about textiles might inform an approach to 3D printed ceramics, and of course ideas about the history of ceramics in architecture might inform an approach. And of course, again, why is any of this important? Well, I'll finish by saying that architects must engage with additive manufacturing beyond it being a technological pursuit. We must not forget the history of materials we use and the architectural stories behind their expression. Thank you.
Thanks for that really exquisite presentation, Susie. Are there some questions? Maybe you didn't talk so much maybe about how the in the first column example, how the toolpaths were defined in that. You spoke a lot about the jointing and also the overlapping, but the exterior expression of those columns. Would you be able to talk a little bit about those?
The black one. or the other one?
No, in your first column example.
This one?
No.
No.
This one. Yeah.
How they were developed, the exterior ones?
Yeah, so they're very articulated. The geometry you are.
Well, yeah. So one thing was about this idea of the textile reference and the weaving kind of nature of clay. So I wanted to start with this kind of very basic interpretation. But the other thing was about this idea of the seam being an element. So I embellished the seam at that point, and also made the decision to do this kind of spring-like or coiling, because what it does two things. One, it shows you that each piece is bespoke, so it's not just kind of standard elements, but also it gives this idea of tension. So although I'm not relating exactly to what's happening with the steel underneath, there's an idea that there's this feeling of energy or movement in the column. So on the outer layer, this is something that's all changing, but the inner piece always remains the same.
Yeah, thank you very much for showing this beautiful work and sharing it with us. I'm impressed about this strategy of putting the things together into the kiln to let them shrink together. How tricky was it to make sure that they fit around the steel column? Do you work with tolerances there, or do you kind of slowly approach towards the optimal diameter?
I mean, it's all about craft and trial and error. I don't use spreadsheets or algorithms or anything like that. I obviously look at what the clay mixture is. I know the water content, and then I measure the diameter on the screen, and then measure the diameter of what I come out, and a few tests of this, and then I've got what I need to do. So it's really just about making a few tests.
And would you need to repeat those tests if the geometry changes of that cladding?
Yes. Not the geometry of the column. Even if you have a flared piece at the top, the shrinkage is still going to be the same. But if you change the profile, then yes. Yeah.
Thank you.
If there are not further questions, thank you. I would just introduce Vittoria while she is getting prepped there. Vittoria Laghi is a lecturer at the Massachusetts Institute of Technology, and she's a postdoctoral fellow at the Structural Design Department at the University of Bologna in Italy, and also a visiting researcher at TU Braunschweig here in Germany. And her focus is the structural applications of 3D printed steel. Thank you, Vittoria.
Thank you. Thank you for the introduction. So, good afternoon, everyone. Thank you for the introduction again. Well, let's just move here very quickly. As was previously introduced, I'm a research fellow in multiple affiliations. So I'm currently at MIT Boston, but I'm also a researcher at University of Bologna, Italy, and a visiting researcher at TU Braunschweig. my whole research is about how to apply steel 3D printing in construction on multiple levels. And very recently, I've also moved towards other materials and other construction materials. But my background is actually as a structural engineering. So I am a structural engineer indeed. And my previous background was an earthquake resistant design. So it's kind of, I was just jumping into additive manufacturing construction for my PhD. So I will just move very quickly to give you an overview to metal 3D printing and construction. I know that like most of you maybe already know that. So over the last decade, metal 3D printing and construction was paving its way first for small connections and very few details in high-end and high-appealing architecture applications. But only over the last 5 years or so, there was the beginning of applying wire and arc additive manufacturing, so an arc-based direct energy deposition, to increase the scale of applications. So as you probably already know, so wire and arc additive manufacturing, it's a weld-based additive manufacturing technology. So it makes use of off-the-shelf welding equipment mounted on top of a robotic arm, and it allows to actually increase the size of the printed element up to a few meters of height and several meters of length. So this is, of course, one of the advantages. So, of course, it's a fast production, but also, ideally, there is no constraints in geometry to be printed in shape or size, and high resistance of the material to be printed. Of course, there are still issues to be tackled. So, the lack of material characterization and mechanical predictions in terms of the performances, and current standard design guidelines. So why making use of wire and arc additive manufacturing construction? So one great advantage is to actually make use of these freedoms. So the idea is that you can ideally create geometries and use material only where it's needed. So make highly efficient structural elements by severely reducing the material use. On the other hand, you need an interdisciplinary effort to do so. So it's not just structural engineering anymore, but you actually need to consider fabrication, design, testing, verification, and robotics. So what was my aim during my whole research was actually to try to draw guidelines, structural design guidelines for wire and arc additive manufacturing elements. So conventionally speaking, Eurocode's current standard building codes make use of conventional approaches, so partial safety factors and design values that are calibrated, accounting for an isotropic behavior, linear elastic material, and ideally like a deterministic geometry, meaning that your geometry is ideal. This is not true for WAM. This is not true for additive manufactured pieces. So one way to go would be to go with advanced numerical modeling. So having a whole digital twin of your entire structure and perform what it's called design by testing. But this is not feasible for every type of project. So it can be done for very high-end projects, but not for everyday use, let's say conventional use. So my idea was actually to adapt the conventional design approach to WAM. So how to do so? Well, you first, of course, recalibrate the design values and the partial safety factors. You account for the anisotropy of the material once it's printed, and you also account for the geometrical irregularities. So this is a little bit of an overview of my previous work on WAM. So we started 6 years ago at the University of Bologna, Italy. We started by material characterization because we honestly first wanted to know how this material worked and how much it would get in terms of strength. I mean, we're engineers, so we really want to know in the end if it's strong enough for our constructions. The result was surprising for us because we didn't expect back in the days that the material would be so high anisotropic. I'm talking about stainless steel, and in particular 308 LSI. And in this case, we then matched our results also with the metallurgic department, and we actually saw that it was all in terms of the microstructure. The microstructure for these layer by layer deposition created this grain orientation, and so the grain orientation was what made the printed stainless steel piece to be highly anisotropic, and in particular to be orthotropic. So we then could predict the material by creating an orthotropic material model, and we could then engineer our elements by taking this into account. Not only that, so of course, as I said before, WOM elements are highly irregular in terms of the geometry that it's printed. So there is an inherent surface roughness, lack of straightness, but also thickness variation, diameter variation, geometry variation. So of course we need to calibrate that and to characterize that properly if we want to then make assumptions for our design afterwards. So we did that through 3D scan techniques, predictions, finite element modeling, and we tried to came up with strategies to, again, make use of that for our design purposes. And here comes with the design. So first guidelines were drawn for some companies that we partnered with, but not only that, we actually were willing to, to also open this up more for maybe ASTM or like future, standard guidelines for additive manufacturing construction. So the idea here is really to recalibrate and recreate like design values, characteristic values of the material strength based on the anisotropy of the material, and also create possible solutions to overcome this real inherent geometrical irregularity by having volume equivalency to have like a uniform geometry along the piece. As I said before, so we created like an orthotropic material model. So we were also able to engineer this material by creating like optimization studies for optimized, efficient beams. In this case, this was a case study on new optimized IPE beams. We called it a blended optimization in the sense that the pure topology optimization algorithms are blended by having, like within our basic principles of structural engineers, manufacturing constraints, anisotropy of the material, and final use. So the final result was actually able to sustain different load cases and different boundary conditions for real case applications. This is just like a hint. So one idea that we had was to actually create a first prototype for an integrated mobile 3D printing system, which is able ideally to 3D print on the element while moving on it. So it's actually currently under patent protection in Italy, and we are quite proud of this like first small rabbit over there. These are just some of the projects that for which we were able to actually grow this research. I would like to just point out the address, which is the second last, and it's a Erasmus Plus project to create a course on additive manufacturing, and the TRR 277, it's additive manufacturing construction. It's a collaborative research project from TU Braunschweig and TU Munich, and it's really just on additive manufacturing construction on multiple ways. Now moving to the core of my presentation, so dot-by-dot printing for lattice structures. Dot-by-dot printing is one WAM technique, so the idea is rather than going layer by layer, you're going towards multiple droplets of molten metal, one on top of the other. So the idea is to create grid shells, grids, bars, and lattice systems. There are, of course, issues to be tackled. So, of course, there's the influence on the build angle. So similarly, but not really to the anisotropic behavior. In this case, the higher the build angle, the higher also the geometrical irregularities and the lower the mechanical properties. So this is, of course, needs to be taken into account when you are designing grid shells and lattice structures. But why doing that? Well, of course, there's a huge chance of having, again, like exploit this use and like this freedom by creating like highly efficient elements by reducing the material use severely. But of course, there's still like the current issue is the long printing time. Why lattice elements? Well, we all know that they are highly efficient. So at the micro scale, so at the scale of the single material, we all know that like lattice elements are well renowned for high stiffness and low material use. At the macro scale, as engineers, we all know about truss elements and truss systems, and these are, again, very good for the high stiffness and low weight, so low material use again. So our idea was actually to scale that up to the mesoscale, so to the scale of the single element. And we could do that only thanks to WAM, because that way we were overcoming the issue of the connection between the single elements at the macro scale, but we were also increasing the application use of the lattice elements at the micro scale. So we started this research in 2018 thanks to MX3D, where I was intern there. The first idea of the diagrid column was actually awarded the 3D Pioneers Challenge 2021 with a special mention by Autodesk for the design. And we continued our research at TU Braunschweig, and very recently we also presented a patent in Italy. We knew that we needed to tackle the issue of different build angles and hence different material properties and different geometry, different irregularities in terms of geometry. So we first characterized the 3 types of inclinations. So the vertical ones, the bars printed at 10 degrees and the bars printed at 45 degrees. 10 degrees was actually one of the lowest possible degree angle, and 45 degrees was actually the highest one, up to which the quality was not really feasible for construction. So moving fast, the experimental tests were actually carried out first on the geometrical characterization. So again, of course, we first wanted to understand what were the diameter variations and the lack of straightness, and we characterized the eccentricity of these bars. Of course, no surprise, the one with the higher degree, the higher build angle, resulted in the higher irregularity. Same goes for the mechanical properties. So of course, a higher build angle resulted into lower mechanical properties. But now moving to the fabrication, because it's the thing that I think you would like most. So as I said, there are different ways of producing lattice elements at the mesoscale. So you can either just do an external diagrid or also do a full 3D diagrid. It depends on, of course, the type of stiffness that you want to achieve. The printing time can be long, that's for sure, so you need to also consider that, and the manufacturing constraints. So as I said, maximum inclination of the bars, but also the limitation in the maximum free length of the single pieces to avoid local buckling. The organization is drop by drop, so dot by dot means drop by drop, and each single drop of molten metal results in a sequence, of course, of rules for the robot. So you need to tackle the offset of each single dot, but you also need to understand what is the waiting time between single dots. Cold metal transfer is of course preferable, as well as high accuracy of the robotic arm, because of course, given that it's a dot by dot system, so each single drop you have to have an accuracy on your the positioning of your robotic head up to 0.5 millimeter, both in terms of on the plane, but also in terms of layer height. Now going to the case studies. The first one was actually the diagrid column. I would have hoped to actually tell you that you could have seen that in the MX3D booth. Last year and the previous years, it was always there. Not sure why this year that I'm presenting this is not here. But anyway, I hope you will see in multiple pictures. Anyway, this is actually a half-scaled column. It's a 2 meter high and 25 centimeter in diameter. It was really the first proof of concept of a diagrid element that could be printed and could actually have very good utilization factor while having a reduction into the material that it's used, so a reduction in weight. The further case studies were developed at TU Braunschweig within the TRR 277 project. So we actually tried multiple experiments and small prototypes, smaller scales, until we wanted to go big. And we actually created the first base part of a proof of concept of a 12 meter high 3D diagrid pillar. of course, it's not, I mean, it's just a proof of concept, but it would be feasible to print it in pieces. Last but not least, it's something that I'm very proud because it recently received also the Iconic Award here in Germany for the disruptive concept, and it's the so-called flow wall. So the idea here is to combine different additive manufacturing strategies. So in this case, WAM as a reinforcement and shotcrete 3D printing as actually the concrete matrix to create adaptive cost line protection systems. So in this case, we are actually making use of the freedom in the geometry to be printed, but also combining the use of two different additive manufacturing techniques. So what's next? Of course, this is just the beginning to me of applying metal 3D printing at a very large scale. I see here at Formnext that there is an increasing interest in WAM, which I'm very happy to know of. But I think that in this case, sky is not the limit, so we should also dream bigger and go bigger. So with that, I also thank you. And this is just a list of significant publications. So thank you.
Are there questions in the audience? Yes, one here.
Hi, thank you very much, Victoria, for your amazing work as usual. My question is, would you ever think about, say, distributing the thickness of the actual droplets? So say, adding more droplets in a specific spot to increase the thickness of the struts, and use this as a method of, say, having more, say, functionally graded materials as lattices? Or is it something you haven't looked at?
Yeah, no, that's a very good question. So let's say not just regarding dot by dot printing, but in general, I think that like for WAM as application, rather than just going very big into the fabrication, we should also consider using a sort of hybrid manufacturing. So exactly, like stiffening maybe like conventional members by just applying WAM where it's needed. Or yeah, why not? Also for grades, I think it would be used for retrofitting or for functionally graded, as you said. For the moment, it's kind of hard to print the bars at different diameters, so like to actually have like a variation in diameters and so the thickness of the lattice element itself. But I think you can also work on the density of the die grid, which is something that it's way easier to actually design.
Okay. Yeah. Thank you.
Sure.
So if you have dot to dot a die grid or in what way are you limited by the machine itself? So is there innovation like with, if you have a die grid, you have like 50 points, would you not need a machine with 50 points in the same time? Or is there work in this direction as well?
Yeah, I mean, I think there is for sure growing interest in this, like in the dot by dot technique. So I think like there should be also like some advancement in the fabrication. So currently what we are doing is to go like each single layer. So like, let's say that like each single cross section has 50 points, then like you're printing 50 points, but maybe you're optimizing the path planning so that like you're reducing the motion of the robot. And so you can optimize that. And so you're reducing also the printing time. But yeah, for sure, there could be limitations that can be also overcome quite easily. So like you can maybe weld pieces together afterwards. And so like you can actually increase the scale of your printed part even more.
Can I ask one more question?
Yeah.
So if you look at relativity space, are they using WAM as well? And are they using one nozzle, or have they solved some kind of economics puzzle?
Do you mean in space?
So they print steel rockets, basically.
Yes.
Do you know them?
Yes, I know of them. I don't know the project personally, so I think there is for sure also there are some advancements that maybe they're not disclosing yet for for the public. But again, also for aerospace, I know that there's like an increasing interest, especially for like this way of like reducing the material use and like looking for like a reduced weight of the pieces. So that's for sure. Not really sure about the fabrication though.
Let's find out. Yeah.
Maybe one question just to connect a little bit to the conversation of Matthias's presentation actually earlier. The question of do you see retrospective or retrofitting potential for this? So rather than making entirely new structures to go in and adapt existing structures or correct or to fix?
For sure. So like one way to me to exploit the lattice meso elements would be to retrofit maybe like on a on-site fabrication the current columns for existing buildings so that they might need, you know, the external steel cage for increase the strength of them. But not only, like as I said before, you can also make use of WAM to increase maybe like the stiffness or the strength of existing members, existing steel members where it's needed. So yes, that's for sure.
If there are not further questions, then we will close this session. Maybe I hand the microphone over to someone who is more informed than I am about the schedule. Philip.
We're just a tiny bit. We're a tiny bit over schedule. Shall we shorten the networking break a little bit and resume the program 15:50, 10 to 4? We'll continue with the next session.
All right, everyone, welcome back to this last session. I'll be your moderator for this one. My name is Olga Ioannou, very hard to pronounce. I'm Greek. I'm also assistant professor at the chair of Building Product Innovation at the Department of Architectural Engineering and Technology at the Faculty of Architecture and the built environment of TU Delft. Now, I'm not an expert on additive manufacturing, but I've been monitoring your discussions and presentations very closely today, and I'm very happy I was invited to join. Mostly because we look at things from the circularity perspective, and it's been very enlightening to see all these things you are developing. So here's some food for thought. Maybe, Philip, you can help me how to do this. Yes. So we are an academic institution, and therefore our task is not just to develop the technology, which is of course now taking over, and in this symposium is probably the most relevant topic, but to also see it in another perspective, that is the perspective of the values. So while you were presenting and discussing things today, the thought was at the back of my head, what is the relevance? What does this technology, this product offer to the world? So as an academic institution, this is what we do. We try to contextualize research, but also initiate research in a way that it is operational, instrumental to the rest of the world. How do we do that? At TU Delft, we have two forces. That's why I named the presentation the Circular Forces. On the left, you see the CB Hub, the Circular Built Environment Hub. On the right, the Circular Impulse Initiative. So to begin with, the CB Hub is a group of 60 to 70 faculty members, researchers and professionals, currently working in the field of circularity, but at different scales. And therefore, collect evidence from different research projects that are currently running for the school. We have a portfolio that reaches something like 8 million euros or something like that. So this is where you can find us. We have a website, and on that website, you'll see the research projects I referred to, but you will also see what we as a hub produce. So we take all these disparate, fragmented pieces of input coming in from that research, and we are trying to make sense of how that works. We're trying to create a coherent narrative between departments that will allow us not only to get the most out of what we're learning from our research, but also systemize it in a way that it becomes instrumental for education. So you can't see this moving, but on the left side you see now how we have currently modeled circularity in the built environment as manifesting across 6 scales and an equal number of aspects. You see the Atto ring. On the right, if the GIF could play, you would see how these different pairings of the scales to aspects manifest in the built environment. Oh, can you? Okay. So, yes. Apart from making sense of what is incoming input, we are also trying to create a vision for where we want to take education in the future, because after all, we are educating the future professionals. And in that sense, we have created for circularity a list of what we now call the circular learning objectives. And through these objectives, we try to match learning activities and also learning materials. I'll tell you more about this as I move onwards. On the right side of the slide, you see our position paper on education, the way we have now framed things, the relevance of circularity in our way of thinking, but also in our programs and our future steps. Education is very important to us. Besides the on-campus education, we have a series of online offerings, either in the form of MOOCs, and you see here several on top, but also professional educational courses that we run with the CBE Hub on the specific scales that I've identified before in the Scales to Aspects model. And here you see 2 profit courses currently available, one at the scale of products, circular building products, and one at the scale of regions. And what you see here on the far right is our professional training programs, because we realize the industry's need for further training their employees, and therefore we devise shorter versions of educational models that focus on a specific topic, may it be remanufacturing or facade logistics, and we run training sessions, 2, 3, 5, depending on the type of topic, with specific employees of specific companies. We also run a new summer school, and that's has just been established. We ran the first summer school on circularity in the built environment this July. We've had more than 40 people joining in from around the world, but also from different age groups and different professions. So there were bachelor and master students, but there were also developers, consultants, and people actually programming education in other institutions in the Netherlands. Right side of the graph, there's a Circular Impulse Initiative, is a newly established program that aims to create new resources to help facilitate the integration of circularity in the school curricula. And you see here that out of this program that is running for the next 2 years, I think, we've developed a series of actions that focus directly on how to make this possible. And we have now these 4 new platforms, let's say. I'm responsible for the 2 on top, Circularity for Educators and Educators for Circularity. Because in our quest to disseminate circularity across the curriculum, we encountered some resistance from professors and tutors, mostly not professors, that come from practice and don't have a full understanding of what circularity is, and therefore somehow present a barrier to the implementation, the further integration of circularity in courses. So we've developed a series of resources that aims particularly at this, targets particularly this group, with the aim of training them to become better, more efficient in teaching about that. But it's not just that. Through that platform, we address also the institutions and the tutors of institutions that are not TU Delft. Because from our experience from running the MOOCs, we realized that we are kind of leading this discussion in circularity. We're very strong at it, and that there's many institutions and many tutors in other countries that can benefit from that. So instead of just sharing our content, we created the second platform, Educators for Circularity. So here's the first one. These are the research. It's a cross-departmental effort, so there's people from all departments of the school. And this is the second platform, Educators for Circularity, that opens up to sharing experience, not just expertise. And there you see people who have contributed in the course, in the content of the first platform, actually initiating these courses on topics related to the content they've shared. And that is open and freely accessible, and everyone can join, and everyone can also pitch a new topic for a discussion should they feel the need to. So 2 things. One is that as an academic institution, we take our role very seriously as to investing everything we do with relevance and values. Second, we are at a point where we've started identifying not just the incoming, the value of incoming research, but also future topics for the research. Where do we want this research to go? And finally, we make this open call to everyone involved in circularity or with an interest or invested in the topic to join us and help us create a better understanding. It's not a one-man show. This is something that requires we all work together. And I'm going to close with this. This is, again, a first-time thing, a first-time event. We've just had the first symposium in architectural education in times of uncertainty, we called it. It was very much related to circularity. One day was dedicated to how we teach circularity. But we also wanted to create, to initiate a discussion about teaching and learning in complexity. Because I know there's no definitive answers about what circularity is, how it manifests, how it is measured, how what conditions it. We have some indications, but not a full knowledge of it. And what is more, it's becoming increasingly more difficult to actually come to a point where we can say, oh, this is a circular project. Oh, hey, this is a circular building. So therefore, how do we teach? And the good thing about this, and something, the main takeaway that kind of stayed with me was that whatever we do, our students are practicing hope for us. And I think we had this discussion yesterday with some of the people we sat together. And we are very happy to be doing this. This is one source of fulfillment for us academics, that we are educating the people who bring back hope. So with that, I leave you. And I'm going to introduce there is hope in the next 3 presenters. So Hedwig Heinzmann She's co-founder and creative director of Actual, a company that produces interior objects and partitions? No, yeah.
Finishes.
Finishes.
Yeah.
So, Hedwig,
Thank
the floor is yours.
There you go. Yeah, very excited to be here. Thank you all for the invitation. It's been a great day so far. I've really learned again a lot. And the coming 15 minutes or so, I will explain you about what we do at Actual. Indeed, I'm Hedwig Heinsman. I'm the co-founder of Actual. I'm trained as an architect at the TU Delft. I used to run an architecture firm called DUS Architects, DUS. And some 10 years ago, we built one of the first large-scale 3D printers. And some 5 years ago, we decided to open up our technology to basically all architects and designers out there, to really share our know-how and enable everyone to really create circular and tailor-made interior and architectural systems. We called Actual because we really would like to actualize people's dreams, ultimately, hopefully, really democratizing architecture. And it starts with AEC because we cater to the AEC industry. What most people probably don't know is that we really are two companies, two legal entities. On the one hand, we're very much software focused. So there we do product development of all our tools and services. And on the other hand, we have our in-house 3D print facility in Amsterdam. We have 4 robots there. I'll talk more about it later. This is probably known to you all, but still it's really a major problem. 40% of all global carbon emissions roughly are caused by our industry, and almost a third of the world's overall waste. And what probably not everyone knows is that interior architecture might be a bigger problem than structural architecture. And I don't have all the data yet to back this up, so let me come back here next year. But every 3 to 7 years on average, interiors, you see it here all around you, you hardly see the structure, they are taken off, thrown to waste, and this is resulting in a massive amount of waste. We're talking also a 2 trillion industry here, $2 trillion, perhaps even more. And what we as Actual focus on are really all those parts. So it's everything non-structural. It's basically the items, the stuff that has a lifespan of 5 months, up to the facade elements that have a lifespan of, let's say, 50 years, and everything in between. And what is really interesting is that actually additive manufacturing coheres really well with circular manufacturing, because you can imagine that you digitally design something, it's 3D printed, it's in use, and in the meantime, we have all the data in our database. After a while, the client, let's say a big retail brand, wants to dispose of it. We take back the product, it's shredded, and it can be reprinted. But in the meantime, of course, we've gathered more and more know-how, so we can create a better product. And this is basically an infinite loop that we can keep on doing. So on the one hand, we have a material recycling loop, and on the other hand, we have a data-driven design feedback loop. And by combining this, well, we think we found the holy grail of circular manufacturing. Our production facility, we have 4 robots operational, about roughly 50 square meters we can produce in one go. Oops, sorry about that. But we also manufacture via partners. That's also why I'm here. Some of my colleagues are also here today to really meet up with production partners. We have 2 partners connected in the Netherlands, and now we're also actively, especially looking for production partners in the US. We cannot do this alone. And we also partner with material partners. In the past, we've also really tried to develop materials ourselves. We've collaborated extensively with Henkel. It's a large multinational, you probably know them, they're German-based. We developed a plant-based plastic with them, but we also now have a global partnership with, amongst others, Tetra Pak, so the drink carton industry, and we also print with recycled polypropylene. I think we've done over 100 large commercial projects over the last 5 years with renowned architects and renowned brands. And also what I'm quite excited about is that they start to get acknowledged more and more. We've had 2 articles in Forbes, one 2 months ago where they called us the ultimate upcycling approach. Read it. How does it work? I already explained it a little bit. So we have our online tools and services. We have a dashboard where you can upload your floor plan, for instance. Then a fitting design is generated, it's shared back to you. A 3D print file is created by us or by one of our partners. It's very easy to install by a contractor, so basically it doesn't require any know-how about installment. And we make sure that after use the product is taken back. This goes in two ways. I will also explain a bit more later, but you either get a deposit when you bring it back yourself, or we take it back free of charge. And then this basically repeats. And we have two offerings. On the one hand, we have furniture. So that's really loose objects that you can just buy basically not off the shelf, because everything is made on demand, but you can just buy directly. You can also customize the items yourself with our online configurator. And we have systems, and they are really on the scale of the building. So I will run you through a few items just to explain you a little bit how it works. So this is, for instance, 3D printed woven wall paneling. We call it a weave. And this is an example of how Nike used it for a project in Oxford Street. It's still there. I think this was made some 4 years ago. But of course, what's great here is that after use, we can take it back and it can be recycled. This is one system. They applied it here in a very sort of vertical way. But this is the same system, the white ceiling you see here, but applied in a very different way. This is the temporary House of Parliament, House of Representatives, I should say, in The Hague. The traditional Dutch parliament from the 17th century is undergoing major renovations. In the upcoming 5 years, the entire parliament is now in this building. And ZEC architects transformed this building, and in order to sort of give it a bit of an entrance, they made this canopy. So all the white panels here, they are based on the same system. So you see that although it's really one identical system, it's very easy for the architect to totally configure it and make it their own and give it really a different shape. Because the panels are a little bit flexible, it's almost like a fabric. You can really also create very interesting curves. I won't go too much into detail about all this because I think this is all super apparent for everyone here. But what of course is really nice is that we can really create custom mounting solutions. The architect will really decide where they'd like the panels to have a bit more sort of open structure so that the light could come through. And this was all very easy to embed. And then the result was there. And also here, 5 years from now, all this will be taken back and it will be recycled. This is all made out of a plant-based plastic, by the way. This plastic is very easy to color. You can do it in really any color as you like, and it's also a little bit flexible. So also based on the required properties, we decide which plastic we print with. But this is an example of the same system, but on a very small scale, really the consumer scale. And you can also just really yourself buy it in our web shop and configure it. So this shows just with how one system you really can create an infinite amount of instances, so to say, tailored to your taste. Another example on a bit bigger scale, this is probably known to a lot of you because this is by Grammatio Köhler at the ETH. And what we find very interesting is that there is, well, you saw it today, there's so much innovation happening at universities, and not always it makes it outside of the university. And what we like to do is really be a platform for designers and architects. These panels, they were initially developed for the ETH, for the Sound Lab. And what is really interesting is that Grammatio Köhler, they developed an acoustic algorithm. So the waves, they really have, they make sure that you can really create optimal acoustic diffusion. But what is interesting that this is also a new economic model because we now sell these panels via our platform. And this is a project in the Netherlands. It will be finished next year. This is an old generator that will be refurbished. You see it here. And also this is a project in the US that will be built next year. So this also shows that, now this innovation is also really making it into the real world. Some other examples, these are for instance blinds. We use them, a lot of hotels, for instance, use them because it's really easy to really create custom configurations in relation to light and shade. So you see some examples here. This is, for instance, in a restaurant in Amsterdam. But this is, again, the same system applied in a very different scale. For instance, Patricia Urquiola, the designer, she used this for a fair design for the Salone. It was also at Orgatech, I think, a month ago. And also for fair design, this is really interesting because now these panels are taken back and they will be shredded. So there's really zero waste now in this process. Another example, this is by Atelier Bruckner, a German architecture firm. They made the several permanent exhibitions for the Future Museum. So you see this is we call it the origami panel. So it can be bended in 2 directions and thereby you can create really nice, sort of flowing surfaces. And it goes on and on. So I'll try to go a bit quicker, but it's really about small scale, but also about bigger scale. And it often holds the middle bit between fabric and fixed. And what is also very interesting is that you as a user can now really personalize your interior. And especially in workplace design, we see that a lot of offices are very interested in this because it's really a way for them to connect more to the employees. And I realized that this was not such a smart example right now. Sorry about that. But this is the ease with which you really can create your own design. So materials, like I said, as we grow as a platform, we try to partner more and more and not do all this research ourselves. But it did really start like that. So this was, for instance, how we started with Henkel. This was several years of testing and trying until we really could reach a certain quality that we really liked. And now we print with several materials. This is, for instance, recycled polypropylene. We use that a lot outdoors because it's really, it has really good outdoor resistance. And here is a very good here is that this is, for instance, a product that we now developed. It's called a wrap, and it's really as simple as that. So it's a wrap, and you can wrap the canteen like this, but you can also wrap it like this. So architects really have a lot of form freedom. So there will be a lot of products available in this material. Also all kinds of new meeting facilities that are a bit a hybrid between real permanent rooms and more temporary furniture. And what is nice here is that, let's say 3 years from now, maybe you'd like to change. That's doable. Some examples of other furniture. And what is nice about the material is that it has almost it has a tiny sparkle in it. Some people think it's a bit like ceramics or clay. It's really interesting material. Another partnership is with a flooring provider. So we 3D print these segment mats. In our factory, and then they are brought together to the site. They're welded together by heat, and then you get these really big surfaces. And then a terrazzo is poured, but it's not a conventional terrazzo. It's with a plant-based binding material and then real marble stones. So you have a very sustainable floor. And this is, for instance, an example in Munich, also designed by Patricia Urquiola at the BMW Museum. This is with Zaha Hadid, for instance, with Nike in the Middle East. I'll finish in 1 minute. So we sometimes make a little step towards more meanwhile use buildings and follies, although we primarily really focus on interiors. This is an older example of an urban cabin we developed, where we tested all kinds of connecting details. And this is a tiny Bauhaus I heard today, you know, the EU is very much thinking about a new Bauhaus. I'm very much for that. And this Bauhaus was traveling Europe 2 years ago, and it was a 100 years Bauhaus, and all the items were products that we offer as a company. And what is nice, of course, is that you can really create details and ornament and designs that really match and that really have no waste, and it really becomes like a Gesamtkunstwerk. What I really like, and you also can sense it now here on the fair, is that 3D printing is really becoming big. And we also really feel that in our own factory, as you see here. So we're now very much focused on expanding our platform. On the one hand, really connecting the designers with the clients and the products. On the other hand, with the industry, with material manufacturers and 3D print manufacturers. And also now circular recycling is really taking off. I think over 30 projects so far have really been reused, or the material has really been reused. And what is really exciting is that right now we take the next step and we start to also offer our products really as a subscription model. So when you are a client of a certain size, you can actually subscribe to our products. So basically you just rent the material for an X amount of time with an X amount of design iterations. And I think that this is really the future of where we're going. And on a very small scale, some examples. This is, for instance, a collaboration with Hermes. So they chose our Freeline panel system and they created their own chaîne d'encre pattern with it. So this year the kiosk had this appearance, and next year we'll see how it has reincarnated. And this is a bit bigger example. This was a pavilion that we printed for and also partly developed and engineered for the Floriade exhibition, horticulture exhibition in the Netherlands the last summer. This was the UAI pavilion designed by Pragma Architects, and we 3D printed this white claustra wall and as well as the green cladding. This building was there for 6 months, and now it's all gone, and it will also reappear somewhere else in a new, in a new design. I'd like to end it there, and I would like to welcome you to meet me afterwards, and if we don't see each other, meet me online. And thank you.
Any questions? Yes. Over there. Oh, I give it. All right. Thought it was mine forever.
Hi, thank you so much for your talk. I'm really fascinated by the work that you do, and I follow you since forever. And it's great to see you coming from an architecture office to now this brand that's all around the world somehow. I recently saw you in New Orleans, your work.
Oh yeah, only on video.
It was really cool. Yeah. I have one important question, because we talk so much about recycling, and we ourselves use FDM printing with robots, and we see that there's recycling is a great idea, but the printing properties vary once you start to recycle your material. So I was wondering if you can share a bit, if you refresh the material or what you do with it to get this continued great aesthetic.
Yeah, and that's a really good question, and we have. Sorry? And the color. The color, how we do that? Yes. We debate about it internally, because on the one hand we'd like to state that we can recycle infinitely, but the reality of course is that you have to add a little bit of new material. However, the new material is already a waste material in itself. So the Henkel material, for instance, the plant-based material, we can really recycle without adding any new material for about 7 times. That's really its great attribute. However, it's also very expensive. The drink carton material, you have to add maybe 5 to 10% of new material every time you use it. However, the new material is already the waste material. So we still see it as a very positive step towards recycling.
You slow down the chain by a lot.
By a gargantuan multiplier, and this also develops over time. It becomes better, right? So, yeah. Oh, and the color? Yeah, so in certain materials we only have a limitation, and that's all the waste materials. So, but it's still quite a lot, and it's not so, because let's say if, how to explain it? When you use a material and it's being recycled, you as the customer don't get the exact material back. It's just, it's at our partners, and you will get an equivalent of the recycled material back. So you're not limited to exactly your own color or...
But do you have to sort the colors when you do the recycling?
It is sorted to an extent, but some material is also just going in bulk. So the polypropylene, for instance, that's only in gray and black, so it always goes in bulk. And the plant-based plastic, that's really sorted per color. Yeah.
Any more questions? Yes. Here we go.
Hi, thanks. Yeah, once again, really inspiring presentation. Do you use any fiber reinforcement in your materials? I'm assuming any fiber reinforcement in your materials, so glass fiber, carbon fiber.
Yeah.
I assume not, because you're recycling it over and over.
No, there is in the material with Henkel, there is glass fiber in it, but it works really well with recycling. That's not a problem. Of course, it's not so great for the environment, so it's not 100% plant-based. And the other materials, to be honest, I don't know really their chemical properties.
Yeah.
But I can ask and I can let you know. Yeah.
And in the Tetra Pak material, is there aluminium inside? Is it filled with aluminium?
Yeah.
Okay, because this can also work as a tensile element, basically, then kind of like a fiber.
Yeah. I mean, in that sense, it's I could very well relate to speaker before, saying it's also very much an empiric, not like the long story. No, but you know, it's also just an empiric trial and error. So I think what we now mostly discovered with the polyol is that actually the aluminium is good because you get rid of the heat really quick. So that's interesting. I don't know if it's also structurally, it's very sturdy, but yeah.
I have a question for you too.
Yeah.
Now you've shown this as a product, but what does it mean to become a circular entrepreneur? What's the backside of all of this? Has it been easy for you?
No, I think it's a good question, but I fear that we're only at the beginning of it. So probably 5 years from now, I'll be even more tired. And
I will ask you again.
But I think, as an architect, I think we're quite good in designing ecosystems and looking at the bigger picture. And that's really what you don't see here. That is basically creating partnerships with others and collaborating. That's a big deal of thinking circular. So, yeah.
Okay. Thank you.
Thank you.
So our next two presenters are, Daniela Mitterberger and Tiziano Dremme. And they are co-founders of the company MADE, that's based in Vienna. And they're also both PhD researchers at Additive. So, guys.
Thank you. So.
Now? We do? We have time? 10-minute break, apparently. Sorry. You have a 10-minute break. Daniela Mitterberger and Tiziano Dremme from MADE, both PhD researchers at Additive. So, guys, please.
Thank you. Do you have the?
No.
Do you have the click? Yeah. Hello everyone, I hope you can hear me well. Thanks very much for the invite. We are very happy to be here. My name is Daniela Mitterberger, that's Tiziano Derma. And we are showing today a work of our office mate, soil 3D printing. And I will give a quick overview on the research that is behind soil 3D printing, and then Tiziano will give you show you the latest installation that we exhibited at the Biennale last year in Venice, the Magic Queen. The research on soil 3D printing started in 2018, and it resulted in 3 big, large-scale 3D printed installations, and they showcase different steps in the research. So we really used the installations also to move the research further. The first one was Pahoe Hoe Beauty. The second one was Terrestrial Reef. And the third one that we exhibited last year, Magic Queen. How did the whole research start? The whole research started with the question on how we can develop novel fabrication strategies for more sustainable and reversible additive manufacturing processes by using biomaterials and at the same time robotic fabrication. More specifically, we were interested in how we can explore the potentials of low-grade organic materials such as soil. Soils are usually classified through their stratification, which starts at the top organic layer where the plants grow and ends at the hard bedrock of the Earth's crust. Beneath the initial organic layer, clay gives the soil its malleable character that most of you maybe know if you work on clay additive manufacturing. If you look at architecture, we see actually that especially in non-Western societies, earth is a building material that was widely used and is still widely used. So here you can see examples such as Ait Ben Hadou in Morocco or Mugumad huts in Cameroon that use really soil as their main building material. And why is it as a building material so interesting, and was also so interesting for us, was because it has very interesting potential, such as it's very inexpensive, it's abundant, and it's available on site, and it has a very minimal environmental impact. If you look at at the current building techniques that we have with soil construction, we see, for instance, compressed stabilized earth blocks, such as on the left side. We see examples such as ramped earth or cob work. And most soil construction technologies actually consist of cob construction, so they focus on masonry wall structures and they build it up in horizontal layers and using a mix of gravel, silt, and clay. And each layer is then compacted during construction until a desired density and bond between the layers is reached. Of course, we already see that soil is entering, and also clay is entering digital fabrication and robotic fabrication. So you see interesting examples that move the fabrication technologies further that you saw in the previous slides. Projects such as Tekla show how we can, instead of the traditional manual layering, we can use automatic and continuous material deposition to build dome structures. The building that you can see here was in collaboration with WASP, and it used contour crafting and raw earth with a multi-crane collaborative printer. Another digitally fabricated cob structure is the clay rotunda that was finished 2 years ago by Gamazio Cola Research at ETH Zurich, which did not use contour crafting, but individual clay elements stacked on top of each other. And another example from IAC, which showed the placing of stairs and building elements within soil construction. So if you look at all these examples, we see that we can use soil as a sustainable and digitally controlled fabrication technique. However, most research that we saw and in this area focus either on very linear wall extrusion or very dome-like structures. Furthermore, most fabrication processes that integrate earth-based materials with digital manufacturing are not entirely adaptive to new soil types. So most of the examples that I showed you, they use very clay soils, so very sticky clay mixtures. And especially these two limitations, so the limitation in design freedom and the limitation of the research inspired us to push the research in this area further. And we saw that these limitations are very difficult to overcome by standard contour crafting and 3D printing processes of for instance, assembly of clay bricks. Therefore, we were looking at other additive manufacturing processes, such as binder jetting, as an alternative to contour crafting of soil structures. However, they require an extensive research on bio-based binding agents, because of course it doesn't make sense to use soil as a building material, promote sustainability, and then use binders that are not completely biodegradable. So the whole idea of soil 3D printing is to create an entire biodegradable fabrication process, which starts from the material, continues to the binder, but also into post-processing. And the whole idea is that really the structure that we are producing can be entirely reintegrated back into nature or reused as a new building material. Binder jetting, as all of you know, is an additive manufacturing process where a liquid binding agent is deposited onto a powder bed to form part cross sections. And then the loose powder can be removed and you have a hardened interior element. So therefore, this research really proposes a method to combine sustainable biocomposites with robotic binder jetting processes to overcome the current limitations that we saw with constructing with soil and at the same time create complex new geometries and novel organic composites. But of course, for us, it was not only a question of sustainability, biodegradability, and fabrication technology, but it's also a very big question of aesthetics. As soil is a granular material, the research that we are doing really intends to find new mediated forms of manufacturing and computing and new forms of how we can design with such materials that take also into account the imprecision that such materials bring. So really a design process that combines the fabrication method, material properties, a robotic fabrication, and a design logic. As Tim Ingold suggests, matter in contrast to materiality does not deal with precision, similarity, and repetition, but actually with emergence and difference. So us as designer designing a framework, but still allowing the material to move within this framework. So as I said before, a very big part of the research is actually on biodegradable binding agents and finding these biodegradable binding agents. And we started to investigate a lot into hydrogels as binding agents and the relation between soil and hydrogel ratios. And I like to show this example because how we started the research in 2018 was with manual models. So we really tested a different relation between the concentration of hydrogels with the compression of the soil and the size of the corns of the soil. And after we developed or we found the right correlation between all these parameters, we moved further and translated them into, at the beginning, a a multi-robot setup, where we especially focused on the path optimization in relation to robot speed. So that means a gradient related to the amount of binder deposited. So the speed of the robot had to correlate with the specific binder. If anyone ever worked with biodegradable binder, they are very sensitive to parameters such as temperature in the room, such as humidity in the room. So all these parameters have to then be included in the computational model to allow the fabrication process to work in the optimal time. Here you can see actually one of the first videos that we were doing from 2018, where we were working with, you will also to see the evolution we did. So this was our first a prototype that we were building with the robot. Back then we were using a hydrogel that was only liquid when it was heated up. So we actually had to use it hot while filling nozzles and while filling the extruder and extruding it in the right amount of time while it's still liquid. So these are really the first experiments that we were doing to find the right proportions. And you can also see here that a big focus point of us was also testing how we can use different soils with different binder densities and different post-processing methods to increase the precision. So how much can we go towards precision and at the same time still stay within, for instance, printing time. And if you look at soil, we investigated the material characterization through three main areas. The first one is mechanical. the second one physical, and the third one chemical. And these early exploratory experiments indicated that the compaction of the aggregate, so the mechanical, the particle size, so the physical, and the time of deposition and concentration of the hydrogels, so the chemicals, are fundamental factors to determine the hydraulic conductivity between each layer. And why is that important? It's important because how much can we stick the soil layers together? Especially also it's related to shrinkage factor. So soil is shrinking by 10% after printing. And also the overall stability and the behavior, especially when we go bigger scale with soil structures. So soil compaction is an important factor. So after each layer of depositing, we need to compact the soil. It's also important what is the particle size of the soil, how much do we have to sieve the soil to have to allow the hydrogel to sieve between the layers, and also the chemical, so what kind of hydrogels and stabilizers can we use. Here you can see our first installation that we were doing for the Ars Electronica. So the Ars Electronica called us and asked us, can you do an installation? We said, yes, of course. It was in collaboration with the University of Innsbruck, and we produced everything in the big hall at the university. Binder jetting, as I explained before, is loose aggregate and hardened aggregate. So these were the blocks we brought to Innsbruck to excavate there. We had no idea if it was working. We never tried it as big scale before. Thankfully, it was working. So here you can see the first installation that we did in Linz. And after that, we did another one in London at the flower show, where we were part of the flower show, so part of the idea of a garden. And here we started to also investigate how we can include robotic fabrication in these setups with novel soil structures.
Maybe I can follow up with Magic Queen, which is, as Daniela mentioned, is the third iteration that comes after the Paoyo Beauty and Terrestrial Reef. So it is the third iteration of a series of installations we called artificial ecologies. And of course, it's a proof of concept of the application of soil 3D printing on a larger scale. The installation was fabricated in situ from March to May 2021 in the occasion of the Biennale of Architecture. Magic Queen is a performative living architecture. It is a 3D printed earth landscape maintained and nurtured by a robotic arm. This installation is completely biodegradable and is mainly fabricating using soil coming from the neighboring region of Venice and bio-based binders. The structure is presented, as I mentioned, as a multimedia landscape that weaves together robotic fabrication, robotic sensory camera feedback, and a visual and auditive interface. Compared to the previous versions, previous iterations, the research on soil 3D printing was really challenged on a completely different scale and setting. And this specifically refers to development of a larger scale installation, a new robotic fabrication system, an on-site fabrication process, and a completely new biological binder. Specifically, in terms of scale, we refer to a biofabrication of an overall structure of 95 tons of compacted soil, constituted by 51 3D printed units with a height range of between 300 to 2,300 millimeters. While in terms of robotic fabrication, we replace the multi-move collaborative system with one single robotic arm. And the two main routines of soil compaction and binder deposition were basically alternated simply using a tool reorientation. This created a more agile environment of fabrication, easier to be handled on site by one single human operator. The new fabrication setup included 4 key steps. First, a human operator depositing the soil aggregates Each bucket was calibrated with an established soil volume. Afterwards, the first routine, robotic routine starts, soil compaction. Here the soil is compacted with a predefined load of around 35 kilos per tapping position. Then the biological binder is deposited following a specific, of course, toolpath planning defined per the current layer. And this routine is repeated until the entire geometry is 3D printed. Of course, once the modules are finished, each single piece is excavated to allow basically a drying process to start. It's important to notice that this was this prototype was the only prototype we could actually do before going on site to Venice. And what does it mean? It means that if we consider the really volatile nature of soils, the biggest challenge was really to foresee the fabrication conditions in the Arsenal of Venice, which is mostly high fluctuations of temperatures, high fluctuation of humidity. And this, of course, is a condition that could have affected in many ways, crucially, the fabrication process and let's say, the assembly of the roller structure. For example, with temperature and humidity variation, an increase on binder viscosity, an increase on weight of the soil due to moisture, and high humidity could have caused a very slow drying process. So this allows us to really develop on site a quite a large number of tools. No? In this case, the quantity of soil per layer was calibrated, not considering different moisture contents. So we developed a simple feedback that we had on the teaching pendant of the robot that allows us to understand how off was each compacted quadrant of soil. And of course, it gives us a plane, an inclination plane, to understand how we could have compensated this. So the compensation actually was done manually by an operator simply regulating the volume of soil. Once the unit is completed, it's safely stored in a drying area. And this is the time where the drying process really starts. No? In this very first phase that approximately lasts 48 hours, allows basically the prints to settle. And allows, of course, the start of a new drying routine, which is the excavation of the 3D printed components. For now, this one was carried by human operators simply by intuitively touching the soil or with the support of a digital model on site. We were confronted basically with two major problems that related to shrinkage and cracking. And we noticed this, that basically we could have overcome these two factors by one was the regulation of a calibration of the center of mass of each components. So this calibration allows us to, for example, have models and units always in equilibrium and possible to be transported. The other one was shrinkage. We noticed that we had majorly a shrinkage on an axial, on the z-axis, by around 10 to 50%. And the way to react to that was to basically deform the geometry along the same shrinkage axis. The dried units were then placed and assembled. For now, the joints were left. We left a separation between all the components. We were really surprised, actually, that somehow all the units dried quite homogeneously, despite the conditions. The soil composition we used was basically 70% peat, 30% clay, with an acidic pH that was tailored to favor specific conditions, such as the growth of very specific wildgrass, or in case of the addition of nutrients, mushrooms. It was very interesting for us because, of course, we could really understand and see that soil 3D printing was enabling a shift towards using materials as inerts to using materials as substrates. And of course, regarding the robotic arm, which is, we call it robotic gardener, it was equipped with two types of tools of sensors. This was the same robotic arm we used for fabrication. It was mounted, reverted. Basically, the gardener was able to sense the landscape and register any changes on the surface of this installation, such as the growth of vegetation, the appearance of cracks. The information was then collected and live streamed on a visual interface so that the visitors could access, let's say, visually to all the data that was collected. The presented project highlights a novel robotic binder jetting process for earthen materials and combine, of course, bio-based polymeric binders with granular soil substrates. The project shows a fully reversible in situ biodegradable construction process for architectural landscape components. You can find additional details on two publications. We are sorry. Oh, sorry. On two publications we published the last couple of years. A third one with the more quantitative data. It's going to be accessible online early next year. Of course, we would like to thank all our collaborators and partners that make us possible to do this project. And of course, all the students that help us during the workshop, the on-site workshop. Eventually, the soil of Magic Queen never left Arsenale. All the material used for the construction was reused to build the Darcy Morelos piece of this year Art Biennale.
And I want to end with an outlook that comes from another project we did afterwards, which is called Silva, and it was for Princess of Asturias Awards in Spain. And in this project, we developed further, especially the sensor units on the robot and the machine learning algorithms to detect plant growth and cracks, because we really believe that if you want to include biomaterials in architecture, in building environment, we need to think further and also understand how we can observe these materials that change over time. And if we understand the robot not just as a fabricator, but also as something that can then be part of an architectural environment, how we can use that to care for the building and not just maintain it. Thank you very much.
Thank you, guys. Questions? Yes. Yeah. Wait.
Oh.
Sorry. Do you have to speak?
Yeah.
Those two.
Thank you very much for the presentation. I have two questions. The first one is about the Venice installation. It's very simple. Can you climb on it? And my second question is about that installation. You mentioned this idea of having the robots as actually part of the life of the building and not just of the building process. But I'm a little surprised at this because for once plants are kind of capable of growing on their own. And the second thing is we've talked a little bit about the idea of maintenance, and it's something humans could engage with to like rebuild maintenance and care relations to the buildings. And I was kind of wondering how you envisioned that proposal in regards to the possibility that life and humans could also do without robots during the life of the building.
Mm-hmm. You wanna?
You can start.
If you can climb it. If you know how to climb it. Now, I have to say, so as with all soil structures, they are not very good on tension. They are very good on compression. So if you do step on it properly, then yes. I have to also say we saw a very big difference. We used different binding agents for the first one and the last installation. And the last one at the Venice Biennale was way better when the big prototype started to move. So it was not as brittle as the first one. I have to say we're still working on that. I mean, we used additional strengthening. So we used chitin, added this. to increase the strength, but as it is with this building process, it's just better on compression. And for the last one, so we used the robot not just to water the plants. We used it also to plant seeds. So when we started to see, for instance, that plants were dying out in a specific region, especially in silver, the robot was used to replant those or to water more or less. So it was also regulating the water content. So if the plant was doing very well, the robot was not doing anything. And if the plant started to die out, the watering was increased in that area. I mean, I really think that these sensor systems have to be developed in parallel to all the material testing that we are doing. Because if we see it, for instance, with the soil structures, a lot of the things we're doing is we test and we do the research on real-scale prototypes at the same time. So that means we need a kind of a supervision system with it that allows us to gather data while producing, to increase the speed we can do research. So I think that's very important part on how we can get bigger faster with biomaterials. Because the biggest problem with biomaterials is we always stay very small scale. And the moment you jump scale with biomaterials, you have so many more problems and so many different problems that I think it's the combination between these sensor systems and biomaterial research that allows us. And my dream is to have a building where the building is also part of the research. So then a robot can send this data and updates, ideally us researchers at the university in real time, how we can improve our research. You want to add something?
Yeah, maybe just quickly on the topic of maintenance. So of course, I mean, I think we need to really start to conceive this idea of maintenance as a more nurturing. So this of course doesn't relate only to the use of biological organic materials, but also relates to a question of temporality of architecture, duration of architecture. So for how long are we building, you know? And this of course it's relates to a question that is directly linked to biological and organic materials. Yeah. To the question of climbing on the structure, I think Daniela gave you the best answer. Yeah.
Any more questions? Yes, Paul. Running.
And it's maybe just a follow-up on that, because I also think the issue of temporality of biomaterials and how they might force us to, or challenge our expectations and force us into new considerations around what a material lifespan should be, for example, is very interesting. But I wonder, and I think there's a provocation here when you, like on the one hand, we are increasingly obsessed by being able to calculate the lifespan of a material and the life cycle of a building, and how and how life spans and life cycles correlate. And I wonder, is that possible here? Or do we need a sort of another perspective onto understanding how those timescales interrelate with one another, or how perhaps biological and technical material cycles might interrelate with one another?
Yeah, I mean, this is a very interesting question for us, especially because we work, these projects are developed within a very strong interdisciplinary environment. And the way how we could relate these different scales in such a different perspective, actually in such a project is by, I mean, first by understanding as well all the disciplines that are involved in such a project, how they can actually contribute in the realization of the project. And the question of temporality, I mean, it is really related to opening the perspective towards, for example, weathering, seasonal changes, and how this can affect really the lifespan of a building. I don't know, Daniela, wanna? Yeah.
Any more questions? I have a remark about aesthetics, because we've seen today, I'm an architect by profession, so we've seen an attempt to use this technology to make very elaborate products And now we see something that's takes so much of meticulous methodology and planning and technology to get the end result that's so indefinite that you can actually make it just by excavating it with the accuracy that excavating can have. So I like this contradiction a lot.
Yeah, I agree. Like this act of excavation, which becomes suddenly very down to earth, but where it's we had a big discussion if these moments of excavation should be automated, can be automated, or in it is actually the moment where you can find yourself again in the structure as this idea as a human that inscribes themselves in human-machine collaborative ideas into the fabrication. And we found that very, very interesting because it's true. You can decide if you want to stop excavating at some point. If you say it's approximate what I want, I ran out of time, it's fine. You can do it very precise. And I also think that a lot of the aesthetics and the emotions that come with this structure is very much this combination of a very basic material, basic principles of fabrication with very high technology. And it's something that we try to always do with our office is this, what kind of aesthetics come out if you combine this very high tech and very low tech at the same time, yeah.
Very well, thank you very much.
Thank you.
Without further ado, we present our last speaker for today, who's unfortunately online. He's Guillaume Habert, and he's associate professor at ETH at the chair of sustainable construction. So, Philippe, do we have him? To your miracles.
Okay, so hello everyone. I'm very sorry not, and yes, I had some teaching and family question that made the mobility a bit difficult. But I will change a bit radically the topic, I think, and discuss a bit this sustainability question and start where do we come from. I would say a few centuries ago, we were, at least in Switzerland, comfortable in our mountains hut, sustainable local materials. The beautiful mountain huts that I was showing initially, this Swiss and we compared a straight wall and a complex wall, and we showed that effectively this like double curved wall, you had effectively an increase in productivity when you were dealing with such complex shape, which you didn't have if you were not dealing with complex shape. You have exactly the same result for environmental impact. It means that you have an environmental benefit of building through digital fabrication if you're dealing with complex shape. So to summarize, you could say, okay, innovation, technology, and technological revolution, they are needed to avoid the collapse of our socio-technical systems. Digital fabrication as such effectively can be characterized as a revolution because it can handle a higher level of complexity without additional cost and somehow is therefore needed. And now comes my question on sustainability, that maybe the bigger threat to our society might not be to collapse from internal complexity, it is just to collapse because the natural system that is supporting us is actually collapsing. And that's what we observe with climate collapse and biodiversity collapse and etc. So let's reframe the question and say, okay, maybe can digital fabrication, by avoiding the collapse of our socio-technical systems, also avoid the collapse of natural systems? And so then the question is, can the extra complexity available through digital fabrication be useful for sustainability? And I would like to show a few work that have been done, a literature survey done by Marcel Assad and others, who kind of compared digital fabrication or additive manufacturing here and conventional construction, and they show, yes, in general, it is better, but not always, typically. And why? It's just because you have relatively, sorry for simplifying the question, but you have very simple drivers. You have an impact of material production, you have a certain amount of material that you use, and you have an impact of the production process. So the only question that you have is that the impact linked with additive manufacturing should be lower than the one that is conventional. Usually what you have is that the impact of the material for additive manufacturing is slightly higher than conventional because you reduce the size of grain, because I mean, for a few aspects, and the impact of the process is also higher because you have a robot. So the question is how much volume you need to reduce in order to compensate this increase of impact. And so that you need to save materials. You have two solutions. The first is to save material through, let's say, structural optimization. Here you have the ripped, stiffened funicular flow systems developed by Block Research Group, where you reduce a lot the volume of the concrete. And you see here that the digital fabrication product is much lower in terms of impact than the conventional one, although the concrete per cubic meter is much higher because you have reduced it, you have more cement per cubic meter, but you use so much less material that you're still better. And the question here is, what is the impact of the production process? Because that's, again, to take the work of Marcela, if you compare the additive manufacturing technique and the conventional technique and look at the contribution of the material and the process, you see that especially for 3D printing, not necessarily robotic additive, but 3D printing, you have an impact of the construction process that is much more important than conventional construction. It could achieve 50% of the total impact. So it means that your structural optimization first needs to compensate the impact of the additional materials the additional impact from the materials, but you also need to compensate the additional impact from the construction process. And there, it means you need to save a lot. That's a study, data adapted from a study from Katarina Kuzmenko and co-authors, and they kind of showed this. It's like for processes where you don't have an intensive process, like robotic assembly, for instance, your volume saving should be around 40–50%. So you need to save 40–50% compared to conventional construction to start to be more climate friendly. For processes which are process intensive, then it's a different. That's the blue one. It's different. If you have a material that has a high impact, then the process contribution is small, and so you're around in the same range. But if the material has a very small impact, then the contribution of the process is quite high, and you need to save a lot of material to compensate the process, which then can reach kind of 80% compared to conventional process. So that sounds to be, yeah, I mean, that's difficult, I would say. The other way of saving material, which is a radically different way of doing, is to what I would call functional hybridization, is to think, and I take the example of this robotic assembly timber roof from ETH that is built by Gramazio and Kohler. It's a structure. It's a structure, but it is also a suspended ceiling. I mean, it has acoustic performance, thermal performance, and finishing performance, I would say. And then we compare a conventional roof and a sequential, and the sequential roof, and you see that the structure, you don't have saving. It means you usually have used as much material as a normal timber frame structure where you have a roof with timber beams. But what you have avoided is the suspended ceiling that you would use normally. So you have an additional function, and this makes your saving. And you make your saving through a specific shape that is providing through digital fabrication. So that's this aspect. Difficulty with that is that it goes against the traditional sustainable principle guidelines of sustainable design, which usually say you have to separate the different function, because the skin, the structure, the services, the staff, etc., don't have the same service life. And when you start to do functional hybridization, well, it means the structure and the technical systems will be embedded in the same element. What is the service life of this element? If you compare this, because it's in wood, even with an uncertainty on the service life, if it's a ceiling or if it's a structure, it doesn't make that much difference. But if it starts to be a concrete, like where you have optimized the structure, you have saved material, and then you try to put technical systems inside. Does your final concrete structure act as a structure, and so will have a service life of 60 years, or act as a technical systems, and so will have to be replaced every 20 years? And then it makes the difference. So to summarize, complex shape can be produced with no additional cost with digital fabrication compared to conventional practice. And as such, I think it allows to handle an extra level of complexity, which increases the productivity and is probably needed to avoid the collapse of our society. In order to additionally support the natural systems our society relies on and be considered as a sustainable technology, you need to use this extra complexity either to structurally optimize your element or to embed multiple functions within one element. And of course, embedding the multiple function need to be think in terms of the fact that they don't necessarily have the same service life. So how do you deal with the adaptability of the future use? And finally, for certain techniques such as 3D printing, the impact of fabrication process is not negligible and requires then even more saving on the material volume than the initial just structural optimization. And with that, I would like to thank you, and I'm sorry for the problem, technical.
Hello, Guillaume. Nice to meet you. Any questions for Guillaume? Yes, around there. The usual suspect. What's wrong with you?
I don't know.
You got me running back and forth.
Hello. This talk was really interesting if you work in 3D printing, because it's a lot of questions I ask myself every day. And I have two things that I wanted to ask you if you put this into account as well. Because we mostly have very complex problems. And I noticed that complex problems most of the time take just longer to plan. And I was wondering if this longer planning period can also be considered like less sustainable, because basically more people have to go to work more often and consume more energy to actually be able to plan. This is the first thing. And the second thing is, if in these digital processes, you most of the time have to touch every point of a structure, which requires energy again. And this touching every point of the structure again is a very energy intensive process that most of the time gets cancelled out of the calculations. So I was wondering, what are your thoughts about this, or if you put this somehow inside your thinking?
Yes, thank you very much. I'm not sure I got exactly your touching of the points of the structure. What do you mean, that you have to calibrate all the time, or? No. Oh, so maybe I first answer to what I understood. The planning process, for sure, you could say that with a digital process, you could potentially save or shorten the planning and the interaction. Usually, we don't consider this as in the environmental impact, especially because you would say these people. I mean, to be very brutal, but you would say these people, they leave, they work, and so if they are not doing this, they would be something else. So it's not so much an increase of an environmental impact because you're doing planning or you're not doing planning. I mean, let's say the activity of the people, you don't integrate that in the environmental impact. What you consider is the energy that you consume, so the electricity, etc., and the material. What the only interest I would say in the planning, which I could see as an interest, is that we are approaching the let's say the cliff of a climate collapse as extremely fast, and effectively these projects, they usually take a lot of time to plan. So the project that we are planning now, they will be implemented in 7-8 years, and to have a shorter planning phase allow probably to be more aligned between what you can produce in terms of material or planning and what you can implement, and avoid to have a somehow nearly outdated technology at the moment of the building is constructed. So if we really need to reduce by 50% of emission in 5 years or in 10 years, you better have a short planning period, even for complex projects. So this is potentially where I would see an interest, is that you have a higher flexibility and you're better adapting to an extremely fast reduction of emission that we, in terms of constraints, that we will have. So that's where I see, but the second aspect of the question, I have to say that I didn't completely get it. I'm sorry.
Now? Okay.
Yes,
so
now I hear you. Yeah.
I don't know, it's a bit tough to explain, but if you, especially with extrusion-based processes, you basically have to imagine you slice your part in layers, and then you have to touch every virtual point of your curve that creates the layer, that creates the part. That's like a lot of movement, like there's so much energy to create this thing. While if you would, for example, make a mold and pour it in a not so complex shape, then you wouldn't have all of this energy. And this is never calculated somehow in all of these things, I feel, because we have quite a big electric bill when we do these things. Yeah.
No, effectively, I think yes. So now I understand, and I think it's exactly what the work of Marcela Saad tried to show, is that but I was fast. But if you look at the global warming potential in terms of the contribution of the total impact from the material contribution, so typically the embodied emission, and the process, which is a little bit what you say, the fact that the robot needs to go all the way through all the curves and the contribution of the process is actually much higher. So usually in conventional construction, you would say 20% on average comes from the process and 80% comes from the average from the material. In digital fabrication is it's kind of the opposite. The 20, I mean, especially for 3D printing, 20% come from the material, 80% comes from the process. So and this is due for this is the combination of two aspects. You use less material, so of course the contribution of the material is reduced because you have saved material. That's one point. The second point is effectively the energy that you put in the robot is much higher than if you just pour the material in a formwork. And so that's why in terms of saving of material, you need to save both the extra impact of, I mean, you need to save material to counterbalance the fact that effectively you have impact on the process, which has been quantified by Katarina Kuzmenko, and which is what I showed here. And they have done kind of a really good calculation on the environmental impact linked with the robotic arm, which is what I showed is like if you have low carbon materials, the contribution of your electricity bill basically it is all the impact that you have, and so if you want to compensate that, you need to save a lot of material or a lot of volume compared to a conventional process. Yes, and maybe to continue on that, it is a little bit the same question as the electric car, is that you're consuming electricity, the environmental impact comes from what type of electricity has been produced. And so if we are, let's say in Switzerland, you have nuclear power electricity, then the carbon footprint is lower. If you're in another country where it's mainly coal-based, then the carbon footprint of your robot is actually, of your process is actually much higher.
Thank you very much, Guillaume. Thanks very much for being here. And well, with this, maybe it's time to close, looking at the time. Thank you all very much for being here for this session, and yeah, see you soon.
Yes, thanks a lot.
No? I hand over the microphone to the master.
See you soon means November next year. Philip, we need you at the stage as well. And Olli, you as well. I'm asked to do some kind of closing words. And as I started, this was starting as a game. Let's see if we get our friends and blah, blah, blah. This family is growing. The interesting thing is we had these 3 sessions, mission meets reality. So it's the first one where we see really big projects. That's something which is interesting. Deep dive research, and then this 3D printing for sustainability, or Olga, where are you? Circularity, that may be more a focus. When I reflect to it, and I'd like to get comments from the 2 of you on that, additional functions. That's something which we are screaming of all the time. Do you see this? Don't worry, this is going to take 7 minutes in total, and then we leave. Well, look at the faces. Shall I not ask any questions anymore? Any comment about this? Just do it quickly. Okay. Do it quickly. So, additional functions. Then, local material and circularity. That is also an interesting impact. We see the circularity hub in Delft being so strong and pushing so much, it really transforms this. So, less transport, less material for structures. And for your question, the WEM family had a good experience in Aalborg by someone analyzing how much energy to need to make these WEM devices versus a milled one. It's not super positive. So we need to be more optimal in optimization structure to be positive in that. And you're right, this is the right question after finding new technology replacing something which is existing. So that's an ongoing business. I also like this local business thing, which I think is something which I quote you in one of the earlier sessions. You said the new original is actually the data. So if you have a platform with all the data, this is going to be global, but then production becomes local. And even more local if you try to use local material and try to use less transport, which makes local business strong again. This is actually working against huge units. And then another thing which we discussed intensively is this new aesthetics. Artistic articulation. Susie, that was your comment. I really liked it because it really, and you see this today, also the first time that intensive, well, at least I thought so, that we have this, there's a certain architectural language to this technology. And we don't know yet. Yes, you're doing these experiments, but we don't know yet if this is the real one. But it's going to be interesting. Printing as a service. You have to explain that one. That was your quote.
Yeah, that's a little bit my takeaway from this morning. There's Waldemar Korte coming, presenting his work as an architect, and he uses a company that prints concrete as a service. And this is something new at the BEAM Symposium that we could, if we look at previous years, then we have a lot of these projects and research where somebody comes from academia, has a robot and a material, and then also prints the bus stop. And now we see that additive manufacturing becomes part of construction, becomes part of larger teams. Knowledge is encapsulated in technology. It can be used. I might oversimplify here, but that was, I think, my takeaway in the morning. And that opens up the floor to new research questions. And we see those research questions. Yeah? How do we work with degrading buildings? This question came up in the previous presentation. And what are our design tools? What are our models to describe biomaterials that change over time? What are the new team members of interdisciplinary research teams that we need if we look at those questions? I think it's great that we could kind of check some boxes in terms of research. They are solved, they made that leap to be transferred into practice, and we can look at new challenges. And I think we will also do that when we invite for BEAM 2023. Yeah, there are other questions popping up, and that's exciting, I think.
Thank you. Yeah, with this, just let me wrap up the day today. There's a lot of people we need to thank in this environment. First of all, I want to thank all of you for coming out here. We're live again. I'm super happy about that. We can be here at Formnext. I like the venue. It's amazing. We had a live stream. We had up to 50 people online who followed us through the day. So thanks again, everyone, for coming. Of course, thanks to all our speakers who made their way all the way to Frankfurt. Even though some of them thought we would do this digitally and thought they did not need to travel, they still made it out here. So special thanks to that. I'm very happy to have all of you in this place again. Of course, there's the editorial team of BAM, BEAM, and all the different variants that we can spell, our network and our conference and everything that we do. Oliver, thanks a lot. Uli, for kicking all these things off. There is Bastian in the audience, made all the way from the US as one of the original contributors. Chris, unfortunately, already left. Nadja, who got us some extra funding from the German Research Foundation. Again, also thank you for that support. There's Jonas, who stayed, like, he's literally the only person who stayed ahead of all the planning at any given moment in time. Thank you for that. Malcolm, who is doing all the photo shoots of today, he's the one designing the little booklet. Thanks a lot for that. And he's the guy for the social media and the website. And then, of course, Darius, who helped us out with microphones, and the entire generative design lab at TU Darmstadt, Marvin operating the camera, Amir and Christine, who I don't think are in the room. Christine's here because they were running our exhibition today and could actually not follow all the talks. So thank you, everyone. Thank you for being here.
November 23.
Is next year.
Yeah.
23rd of November, next year, this place. I hope we get an even bigger room. Thanks.